Hello there, and welcome to Science for Sleep, where curiosity takes a deep breath and wonder settles in like evening light. Tonight's quiet journey drifts through the largest mystery there is, the place where everything we can possibly see ends and something else begins. It's not an edge made of walls or borders, not a cliff you could fall from, but a fading of light, a soft vanishing point in the vastness of space, where even time itself begins to blur. The observable universe, that's what we call the grand sphere of everything that has ever sent light our way, every star, every galaxy, every ancient flicker that's had just enough time to reach us. Beyond that limit, light has not yet arrived, and yet something must still be there. Perhaps more of the same, perhaps something unimaginable, and tonight we'll let our minds wander there slowly, gently, like travellers gazing out from a ship's deck into the dark beyond the horizon. Before we begin, I'd love to know, where are you listening from right now? Is it quiet where you are? Maybe there's a softer light in your room, or a familiar hum somewhere nearby. The night outside is the same one that stretches all the way to galaxies you'll never see, and yet their light touches you, faintly, invisibly, right now. The universe doesn't end at the edge of your sight. It continues through you. And if this kind of slow, thoughtful wandering feels like a peaceful way to end your day, I'd be so grateful if you left a like or subscribed. It helps others find this same calm corner of curiosity. Now, if you're ready, take a slow breath. Let your mind soften its grip. We're going to drift out far beyond what the eye can see, to the place where seeing itself begins to lose meaning. Imagine stepping outside on a clear night. The air is cool, the kind that carries sound softly, and the stars seem sharper the longer you look. Each one is a messenger, carrying light that's been travelling not just for years, but for thousands, millions, even billions of years. When you gaze up, you're not looking at what's happening now, you're looking at the past, layers of it stacked upon each other, as if the universe keeps old memories in plain sight. The nearest star apart from the sun is about 4 light years away. That means its light left when you were 4 years younger than you are now. The light from the Andromeda galaxy began its trip more than 2 million years ago, when early humans were still learning to shape stones. You're not seeing where Andromeda is tonight. You're seeing where it was before there were cities, before there were languages, before there was anyone to name it. And the deeper you look, the older the light gets. The Hubble Space Telescope, and now its quiet successor, the James Webb, can see galaxies whose light has travelled for over 13 billion years. These are not just faint smudges. They're relics from a time when the universe was young, dense and hot, only a few 100 million years after the Big Bang. Their light has stretched as space expanded, stretched so much that it's no longer visible to the human eye, only to sensitive instruments that can feel the faint warmth of ancient radiation. Every time we point a telescope at a seemingly empty patch of sky, more galaxies appear, hundreds, thousands, all shining from unimaginable distances, and even those are just the ones close enough for their light to have reached us. Beyond that, there is more, vast regions forever hidden, because their light is still on its way, maybe never to arrive. This is what astronomers mean when they talk about the observable universe. It's not the whole universe, just the part that can, in principle, be observed from here, from Earth, in this moment of cosmic history. Because light has a speed, and time has passed only so long since the beginning, there's a limit to how far we can see. If the universe is roughly 13.8 billion years old, you might think the furthest we can see would be 13.8 billion light years away. But space itself has been stretching all the while, so the farthest galaxies we can currently observe are much farther than that, about 46 billion light years away in every direction. That's the radius of our observable universe. Everything inside that immense sphere has had time to send us light since the Big Bang. Everything beyond it remains invisible, not because it doesn't exist, but because there hasn't been enough time for its light to arrive. Think about that for a moment. There are galaxies out there whose light will never reach us. Not now, not ever. They are moving away faster than light, carried by the expansion of space itself. It's not that they're breaking the cosmic speed limit. They're passengers on a stretching fabric, and that fabric can expand faster than any traveller within it. So even if those galaxies keep shining forever, their light will grow fainter, redder, stretch thinner and thinner until it slips away beyond reach. From our perspective, they will fade into the dark, like ships sailing over the curvature of a cosmic ocean. And somewhere, far beyond that invisible horizon, there are galaxies that have never known we exist. To them, our entire Milky Way, our Sun, our Earth are unlit, unknown, unimagined. That horizon defines the edge of what we can ever know by light. But it's not a wall. It's not the end of the universe. It's just the end of visibility. You can think of it like standing on a beach, watching the ocean stretch until it meets the sky. The horizon looks like an edge, but you know it isn't. The sea continues far beyond your sight. The same is true for the cosmos. The observable universe is our horizon, not the boundary of reality. What lies beyond it may be more of the same. More galaxies, more dark matter, more space gently expanding. Or it may be something altogether different, where the rules we know start to shift, or where the structure of space-time itself changes. We don't know, and maybe we never will, but that not knowing has a kind of quiet beauty. You might wonder why the term observable universe sounds so modest, almost cautious. It's because it has to be. Every observer in the universe has their own version of it. A galaxy 10 billion light-years away would have its own observable bubble, centered on itself, overlapping ours only partly. The universe looks different from different vantage points, so, in a way, there is no single, universal universe that everyone shares equally. There are as many observable universes as there are places from which to observe. The one you occupy, right now, sitting in your room listening, is a bubble of cosmic awareness, shaped by the speed of light and the passage of time. Our ancestors, long before telescopes, already sensed that the heavens must extend beyond the stars they could see. They watched the constellations drift and repeat, noticed wandering lights, planets, and wondered what might lie beyond them. Each generation's horizon expanded, from the solar system to the galaxy, from the galaxy to the observable universe. Each discovery showed that our world was smaller than we thought, yet the mystery was larger than ever. And that's the strange balance of cosmology. The more we learn, the less we seem to know about the totality of everything. The visible universe may be enormous, but it's still just a fragment, a glimpse through a narrow cosmic window. When astronomers map the sky, they're not drawing the edges of existence, they're drawing the edges of perception. And between what we can see and what we can't, there's a vast in-between. A zone of fading signals, redshifted light, ancient photons stretched to invisibility. This region isn't a sharp cut-off, it's a gradual dimming, where information dissolves into the background of reality. Somewhere out there, beyond the farthest galaxy we'll ever see, the expansion of space carries matter away so swiftly that it falls permanently out of contact. Whatever happens there, we'll never know. And that's not a flaw in our instruments or a gap in our knowledge. It's simply the structure of the universe. You might think of this cosmic edge like a horizon of time as much as space. When we look outward, we look backward. Every additional distance is an earlier chapter of cosmic history. Nearby galaxies show us the universe as it is today. Farther ones show us how it was billions of years ago. The faintest, most distant light we can detect comes from just after the universe became transparent, about 380,000 years after the Big Bang. Before that moment, the cosmos was too hot and dense for light to travel freely. The universe was a glowing fog of plasma, scattering photons in every direction. Only when it cooled enough for atoms to form did the fog clear, releasing a flash of light that has been travelling ever since. we can still detect that glow today, stretched into microwave radiation, bathing the entire sky. That's the cosmic microwave background, the afterglow of creation, the faint whisper from the universe's earliest dawn. So even now, when you close your eyes and imagine darkness, you're still surrounded by light older than stars, older than galaxies, older than time as we usually think of it. It's everywhere, faint but constant, a memory the universe never forgot. That's part of what makes the edge of the observable universe so remarkable. It's not a frontier we can reach. It's a boundary we can only understand by listening to the oldest light still whispering across billions of years. And yet, beyond that whisper, beyond the faint final echoes of the beginning, lies something that light has never touched from our point of view. Maybe it's more space expanding endlessly. Maybe it's a region where physics behaves differently, where constants change, or even where time itself takes on a different texture. Some theories suggest that the universe could be infinite, unbounded, repeating patterns beyond comprehension. Others propose that it might be curved back on itself, finite but unbounded like the surface of a sphere, where travelling far enough in one direction would eventually bring you back to where you started, though the universe's expansion makes that journey impossible in practice. Standing here, thinking about these scales can make the mind feel both impossibly small and quietly connected. Because you, me, everyone, we're built of the same material as the stars whose light defines the edge of what we can know. The hydrogen in your breath, the carbon in your skin, the iron in your blood, they were all forged in stars long ago, scattered across the galaxy, reassembled into living, thinking beings capable of looking back and wondering where the universe ends. There's a kind of symmetry to it, the cosmos becoming aware of itself, even if only in a tiny fraction of its expanse. The thought that there's an edge to our vision, but not necessarily to existence, might sound unsettling, but it can also be strangely comforting. It means that the unknown is not a void waiting to be feared, but an endless continuation of reality's quiet hum. Just because we can't see it doesn't mean it isn't there. In a sense, it reminds us that mystery is not absence, it's abundance. The universe beyond the observable horizon isn't missing. It's merely unlit from our perspective, waiting beyond the reach of our light and time. Every time astronomers push the boundaries of observation, building larger telescopes, refining detectors, peering deeper, they're really extending our past, not our present. Each discovery further back in time reveals a younger version of the universe, and yet, even as we see more, the horizon recedes. It's like chasing the sunset. The faster you move, the farther away it seems. But that's the beauty of it. There's always more to reach for, more to imagine, more to wonder about. And so we stand, metaphorically, at the edge of sight, looking into a darkness that isn't empty but full of possibilities. Somewhere out there, beyond the reach of every photon that will ever reach us, lies the rest of reality, untouched, unseen, perhaps infinite. It's not a place we can go, not a frontier we can conquer, but a reminder that the universe is larger than understanding and gentler than we often think. The observable universe isn't a prison of light, it's a gift. It shows us that there is always more than what can be measured, that knowledge itself has horizons, and that curiosity is the bridge between what we see and what we'll never see. Now that we've reached the quiet boundary of visibility, we can begin to explore what defines it. What is this horizon, really? This invisible edge that marks the limit of what can ever be known? If the edge of sight is where the known universe fades into the unknown, then the horizon that defines it is not a line drawn in the sky, but a concept written in light. It's one of those scientific ideas that sounds simple until you really look at it, and then it quietly unravels into something far stranger. The cosmic horizon is the boundary that marks how far light has travelled since the beginning of time, the limit of what any observer anywhere can see. Not because the rest isn't there, but because light simply hasn't had enough time to reach us. To picture it, imagine standing in a wide open field on a misty morning. The fog softens the world until only the closest trees are visible, the rest fading into grey. You know there's more beyond the mist, but your eyes can't pierce it. The cosmic horizon is like that fog, not made of vapour, but of distance and time. What lies beyond is still there. Galaxies, stars, perhaps entire clusters of worlds, but their light is trapped by the expansion of the universe itself, stretched and slowed until it can never reach our telescopes. Every observer, no matter where they stand in the universe, has their own cosmic horizon. It's personal in a cosmic sort of way, defined by where and when you exist. An astronomer on a planet orbiting a star in a galaxy billions of light years away would have a completely different horizon from ours, centered on their own position, yet overlapping ours slightly. If you could see all those horizons from above, they'd look like bubbles of light scattered through infinite darkness, each one glowing faintly with everything its observer could ever know. We live inside one of those bubbles, floating through a sea of countless others, none of which can see each other completely. The reason for this boundary lies in the finite speed of light and the finite age of the universe. Light, fast as it is, can only travel so far in a given amount of time. When the universe began, around 13.8 billion years ago, it started expanding. Space itself has been stretching ever since, carrying galaxies along like dots on the surface of an inflating balloon. Because space expands, the distance that light can cover grows more complicated than simple arithmetic. Light emitted billions of years ago has been travelling through a medium that's expanding beneath it. By the time it reaches us, the source of that light is much farther away than it was when the light began its journey. That's why our cosmic horizon isn't 13.8 billion light years away, but roughly 46 billion. It's not that the light moved faster than light, it's that the space between us and the source expanded while the light was on the way. Think of it as trying to walk across a moving walkway that's stretching beneath your feet faster than you can move. No matter how far you go, the end keeps receding. The light we see from the most distant galaxies comes from a time when the universe was far smaller, yet those galaxies are now tens of billions of light years away. They've been swept outward by the cosmic expansion, and many are already beyond the point where their light will ever reach us again. This creates a subtle but profound truth. The deeper we look into space, the less we see the present, and the more we see the past. The cosmic horizon is therefore not just a boundary of space, but of time. When you look out to the farthest galaxies, you're not seeing where they are, but where they were when the universe was young. The light from those early galaxies began its journey billions of years ago, and because light speed is constant, that journey takes billions of years to complete. You're seeing a cosmic time capsule, light that set out long before Earth existed, long before the sun was born, long before there was even oxygen to breathe. Beyond that horizon, events are unfolding right now, but we'll never witness them. Stars are forming, galaxies are colliding, maybe entire civilizations have come and gone in the farthest reaches of space, yet their light will never reach our eyes. To us, they are already invisible. To them, perhaps we are too. This isn't a limitation of technology, it's a feature of the universe. The expansion of space itself ensures that some parts of the cosmos are permanently out of touch with others. You could build a telescope the size of the solar system, and it still wouldn't help. No matter how sensitive your instruments, light that hasn't arrived can't be seen, and light that never will arrive is lost forever to our perspective. This means the universe has an event horizon, much like a black hole does. In a black hole, gravity is so strong that not even light can escape. In the universe as a whole, expansion can become so fast that not even light can catch up. There's a radius around us beyond which objects recede faster than light due to the stretching of space, and no signal, no matter how powerful, could ever bridge that gap. Cosmologists call this the cosmic event horizon. It's different from the particle horizon, which marks the limit of what we can see now. The event horizon marks what we will ever be able to see, even given infinite time. Beyond it, galaxies drift away faster than light, disappearing into a cosmic night that will never lift. It's a strange thing, knowing that the universe is connected and disconnected at the same time. When you look up, you're seeing photons that have travelled across space for billions of years to reach you, some from galaxies so far away that their light began its journey before our planet formed. But beyond that, there are galaxies whose light will never make it to us, even if we wait forever. It's as if the universe is full of conversations happening just beyond earshot, endless stories we'll never hear. Still, those distant regions aren't isolated in every sense. The matter that now lies beyond our horizon was once closer, once part of the same connected region. In the earliest moments after the Big Bang, everything we now see, and everything we never will, was compressed into a smaller, denser space. Particles, radiation and energy were all mixed together before expansion carried them apart. That's why the cosmic microwave background looks the same in every direction. It's the lingering glow from when the whole observable universe was once in close contact. The uniformity of that ancient light is a clue to how closely knit everything once was. Even the parts of the universe we can never see again were once right here, sharing the same cosmic neighbourhood. When astronomers study this horizon, they're not just looking outward, they're looking backward in time toward the beginning. The oldest light we can detect comes from the moment the universe became transparent, when electrons and protons first combined to form neutral atoms and light was finally free to travel. Before that, the universe was opaque, a soup of particles and radiation scattering endlessly. That moment of first transparency, known as recombination, happened about 380,000 years after the Big Bang, and the light released then still fills the universe today. It's what we detect as the cosmic microwave background, a faint hum of microwaves coming equally from every direction. That light carries information about the universe when it was less than 1 million years old. Its tiny variations in temperature and density are like fingerprints of the earlier structures that would later grow into galaxies and clusters. Studying it has allowed cosmologists to measure the age, shape and composition of the universe with astonishing precision. From that data, they've inferred that the universe is remarkably flat on large scales, dominated by dark energy and dark matter, and still expanding faster than ever. But the background light also marks the end of our cosmic vision. Beyond it, there's no light left to see, not because nothing exists there, but because the early universe was opaque. The cosmic horizon, therefore, is a boundary both of light and of knowledge. Sometimes it's tempting to think of this as frustrating, a limitation on curiosity. But perhaps it's better seen as an invitation to humility. The horizon tells us that no matter how powerful our tools become, there will always be more than we can know. And yet, that unreachability doesn't make the unknown meaningless. The very existence of the horizon proves the immensity of reality. It's the universe reminding us that the story continues beyond our page, that there are chapters we'll never read, but that are still part of the same book. As the universe expands, the cosmic horizon changes. Right now, the observable universe extends roughly 46 billion light-years in every direction, containing around 2 trillion galaxies by some estimates. But as time goes on, the expansion driven by dark energy will push more and more galaxies beyond reach. In the very distant future, billions of years from now, only the nearest galaxies bound to ours by gravity will remain visible. Everything else will fade away, leaving a dark sky with just a handful of island galaxies drifting in the void. Future astronomers, if any remain, will have no way to see the cosmic horizon as we do. To them, the universe will seem small, quiet, and eternal, with no sign of the grand expansion that once filled the sky with countless galaxies. It's strange to realize that we live in a privileged time for cosmic observation. The light from the early universe is still arriving. The galaxies beyond our local group are still visible, though dimming. We exist in a moment when the universe is old enough for structure to have formed, yet young enough that much of the cosmos remains within sight. Millions or billions of years from now, that won't be the case. The horizon will close in, the cosmic stage will dim, and the evidence of expansion will disappear. In a way, the universe is showing us its secrets now, in this brief cosmological window, before drawing the curtain again. The cosmic horizon is therefore not just a scientific boundary, it's a moment in cosmic history, one we happen to inhabit, and within it lies everything we'll ever know, every star that has ever lit our night, every photon that will ever reach our eyes. It's an invisible dome of possibility, defining our cosmic address. If you could step outside it, you wouldn't find a wall. You'd simply find more universe, continuing endlessly, indifferent to what we can or can't perceive. When you sit beneath the night sky, you're not just seeing stars scattered in space. You're seeing the edge of time itself. Every point of light is a messenger from a different era, a snapshot from a different distance. The cosmic horizon gathers them all into a single panorama, a vast curved surface of light marking the furthest history visible to any being in this corner of space-time. And while it might feel impossibly distant, it's also intimate, because it defines the space you inhabit. The atoms in your body once existed within that same expanding bubble of light. The cosmic horizon isn't out there, it's part of your story, the boundary of your own cosmic inheritance. Beyond it, the universe continues silent and unseen. But within it lies the evidence of everything that ever has been, from the first hydrogen atom to the latest flicker of starlight. The cosmic horizon is not a limit to imagination, it's its invitation. Every question about what lies beyond begins here, at this invisible boundary between light and darkness, between the known and the unknowable. And it's from this horizon that we start to hear the oldest echo the universe ever left behind, a whisper from its beginning, still rippling through space after nearly 14 billion years. The light that fills the universe today is older than any star, older than galaxies, older than the elements that make up the world you're sitting in now. It's a quiet light, invisible to human eyes, but all around you at this very moment, passing through walls, through air, through everything. If you could see in microwaves instead of visible colours, the entire sky would glow faintly and evenly, not from stars or planets, but from the afterglow of the beginning itself. This is the oldest message the cosmos has ever sent, the cosmic microwave background. It began as light from a time when there were no stars, no planets, no dust, no molecules, just a hot ocean of energy and particles colliding so frequently that light could not travel freely. Back then, about 380,000 years after the Big Bang, the universe was a glowing fog of plasma. Photons, the particles of light, bounced constantly from electron to proton to electron again, trapped in an endless scattering dance. The universe wasn't transparent, it was radiant, but in the way a dense cloud glows from within, brilliant yet concealing. The temperature everywhere was roughly 3,000 degrees Celsius, bright orange if you could see it. Then, as the universe expanded and cooled, it reached a threshold. Electrons began to settle into orbit around protons, forming neutral hydrogen atoms. Light was suddenly free to travel without being endlessly scattered. That moment, when light decoupled from matter, was the first sunrise of the cosmos. The light released in that instant has been travelling ever since. As space expanded, its wavelength stretched from visible light into infrared, and then into microwave radiation. What was once a fiery orange glow has cooled to just 2.7 degrees above absolute zero, a faint wash of microwaves filling the universe uniformly in every direction. It is, in a very literal sense, the oldest photograph ever taken, not by a camera but by existence itself. When we detect it, we are seeing the universe as it looked nearly 14 billion years ago, frozen in the moment it first became transparent. For a long time, no one knew this ancient light existed. The idea came from theory first. In the mid-20th century, physicists working on models of the Big Bang realized that if the universe began as a hot, dense state, then it should still be glowing faintly today, its light stretched by expansion into microwaves. They predicted that if we had sensitive enough instruments, we should find a uniform background of radiation coming from every direction. And in 1964, quite by accident, that's exactly what happened. Two radio engineers, Arne Penzias and Robert Wilson, were testing a microwave antenna designed for satellite communication. They kept finding a persistent noise, a faint hiss, no matter where they pointed the instrument. They thought it might be interference, maybe from the city, maybe from a nearby radar. They even cleaned out pigeon droppings from inside the antenna just in case. But the noise remained, steady and unchanging, coming from every direction. When they compared notes with a group of physicists at Princeton who had been searching for the predicted cosmic background, they realized what they had found. It wasn't noise. It was the leftover light from the birth of the universe. That discovery transformed cosmology from speculation into measurable science. For the first time, we had direct evidence that the universe had indeed begun in a hot, dense state. The cosmic microwave background became the cornerstone of modern cosmology, the proof that space itself had once glowed with radiation and that expansion had cooled it over time. But what's remarkable isn't just that this light exists, it's how much it tells us. At first glance, the background seems perfectly uniform. Look in any direction, and the radiation has almost exactly the same temperature, 2.725 Kelvin, differing only by a few parts in 100,000. But those tiny differences are everything. They are the fingerprints of the universe's first structures. Slight fluctuations in density and temperature in that early plasma eventually became the seeds of galaxies, clusters, and all the cosmic architecture we see today. If the background were perfectly smooth, the universe would have remained featureless forever, but those tiny ripples, minuscule variations in brightness across the sky, were enough for gravity to begin its slow work, drawing matter together over billions of years. When satellites began mapping this background in detail, the results were astonishing. The first to capture it fully was the COBE satellite in the early 1990s. COBE confirmed that the radiation followed the perfect curve expected of the black body, a type of pure thermal radiation, proving that it was indeed a relic of the early hot universe. It also detected the first signs of temperature variations, though only in rough outline. Then came the Wilkinson Microwave Anisotropy Probe, WMAP, which mapped the sky with far higher precision, revealing a faint mottled pattern, tiny warmer and cooler spots scattered across the heavens. Later, the Planck satellite improved that map even further, giving us the clearest image yet of the universe as a baby, just a few 100,000 years old. Those subtle patterns are a treasure map for cosmologists. They tell us how much ordinary matter, dark matter, and dark energy the universe contains. They tell us its age, its geometry, even its destiny. From the way those ripples are distributed, scientists have learned that the universe is flat on the largest scales, meaning parallel lines would never converge or diverge even across billions of light years. They've learned that only about 5% of the cosmos is made of the ordinary atoms that build stars, planets, and people. The rest is invisible. Dark matter, which holds galaxies together, and dark energy, which drives them apart. It's strange to think that all this information is encoded in light that's been travelling since before there were stars. Each tiny photon carries with it a record of the conditions that existed at its birth: density, temperature, motion, and together they paint a portrait of the cosmos at its earliest moment of clarity. This light doesn't just tell us where we came from, it tells us what kind of universe we live in. If you could somehow translate the microwave background into sound, it wouldn't be silence. The early universe was full of pressure waves, ripples of compression and expansion moving through the hot plasma like sound waves through air. In fact, scientists sometimes call them the universe's first music. These waves left imprints in the background radiation, patterns of slightly hotter and cooler spots that correspond to the peaks and troughs of those primordial oscillations. In a sense, the cosmic microwave background is a frozen record of that music, a visual echo of vibrations that once filled all of space. Over the decades, measurements of this ancient light have refined our understanding of cosmic history. We now know that after it was released, the universe entered a long era of darkness. The first stars wouldn't ignite for hundreds of millions of years. During that time, there were no sources of visible light, only the faint invisible microwave glow. When the first stars finally did form, they began to reionize the surrounding hydrogen, making the universe transparent again. Their light gradually replaced the darkness, and the cosmos entered the age of stars and galaxies. But the background radiation remained, stretched ever further as the universe expanded, cooling as space grew larger. Today, that light fills every corner of the cosmos evenly. Even in the deepest voids between galaxies, the cosmic microwave background hums quietly, its photons endlessly crossing empty space. In practical terms, it forms a kind of cosmic baseline. Every telescope, every radio receiver, every satellite must account for it, because it's always there, a constant presence, like the faint static between stations on an old radio. If you've ever tuned a television to an empty channel and seen the flickering static, a small fraction of that signal, about 1%, comes from the cosmic microwave background. When you see that random fuzz, you're watching ancient light, photons that began their journey when the universe was younger than a single human lifetime compared to now. It's humbling to realize that something so pervasive, so ancient, and so important goes entirely unnoticed in daily life. You can't feel it, can't see it, can't hear it without specialized instruments. Yet it's everywhere, passing through you, through the walls, through the Earth itself. Every second, billions of those photons move through every square centimetre of your body, remnants of a moment when the cosmos was a glowing mist. They don't carry warmth anymore, just the faintest whisper of it, but they carry history, an unbroken thread connecting the present to the very beginning. This ancient light also serves as a kind of cosmic ruler. Because we know its properties so precisely, scientists can measure how it has been affected by the structure of the universe along its journey. As those photons travel through space, they pass by clusters of galaxies whose gravity bends their paths slightly, a phenomenon called gravitational lensing. By studying these distortions, researchers can map the distribution of dark matter, even though it emits no light of its own. The background becomes a backdrop against which the invisible becomes visible, a universal screen showing the imprints of everything the light has passed. But there's something even more profound hidden in this radiation. Tiny variations in its polarization, the direction in which the light waves oscillate, contain clues about the universe's earliest fractions of a second. Some theories suggest that during a period called inflation, the universe expanded exponentially, faster than the speed of light, smoothing out its contents and seeding the ripples we now observe. Inflation would also have generated gravitational waves, ripples in spacetime itself, that left subtle signatures in the polarization of the cosmic microwave background. Detecting those signatures would be like hearing the universe's first heartbeat, a direct echo of creation's earliest tremor. Researchers are still searching for that evidence. Sensitive experiments in Antarctica and in space are trying to detect those faint polarization patterns. The signal, if it exists, is incredibly small, buried beneath other sources of noise, but the effort continues because finding it would open a window into the universe's first instant, a moment we can only imagine but never directly see. Until then, the cosmic microwave background remains our closest view of the beginning, the earliest photograph in existence. To gaze at the map scientists have made of this background is to look at something both simple and infinite. The colour-coded blotches, blue for cooler, red for warmer, aren't much to look at aesthetically, yet they contain everything. The seeds of galaxies, the measure of the universe's shape, the echo of its birth. Every speck of variation represents regions where matter was slightly denser, destined to collapse into stars and planets billions of years later. When you trace your own existence back through that chain, Earth forming, life emerging, consciousness awakening, it all begins with those ripples in that ancient light. You are, in a very real sense, a pattern in the microwave background, evolved and amplified across cosmic time. What makes the background so moving isn't only its age, but its constancy. It's been shining for nearly 14 billion years, and it will continue long after the last stars fade. As the universe expands, the radiation will stretch further, cooling into longer wavelengths, its energy thinning until it becomes undetectable. Far in the future, when galaxies drift apart faster than light, and the cosmos grows cold and dark, that ancient glow will still be there, stretched beyond recognition, but never gone. It's the one thing that connects every era of cosmic history, from the first atoms to whatever lies ahead. When you think about it, the universe still carries its own memory, not in words or symbols, but in light. Every photon from that first dawn is a record of what once was, moving endlessly outward, never stopping, never fading entirely. To exist in such a universe is to live inside a memory so vast it surrounds you completely, an echo of the moment when everything began to cool enough for light to roam free. And from that faint glow, everything else unfolded. Stars formed, galaxies grew, worlds took shape, and eventually creatures evolved who could look back and realize that they were surrounded by the earliest light of all. This soft radiation, invisible yet omnipresent, is the universe's oldest message, still being delivered, still crossing the void. When we study it, we're not just looking backward in time, we're listening to the cosmos tell its first story. The universe, as far as we can tell, isn't expanding into anything, it's simply expanding. That statement sounds impossible at first, like saying a loaf of bread is rising without an oven around it, or a balloon is inflating with no air to fill it. But that's the curious truth about space itself. The expansion of the universe isn't matter moving through a pre-existing void, it's the stretching of the void itself. Galaxies aren't sailing outward into emptiness, they're being carried apart by the very fabric of space-time. When astronomers talk about this expansion, they're describing something woven into the structure of the cosmos. It's not a force like gravity or electromagnetism, it's a feature of the geometry of reality. Distances between galaxies increase not because the galaxies are flying through space like projectiles, but because the space between them is stretching. The galaxies themselves, and the clusters they belong to, remain bound together by gravity. But the vast expanses between those clusters grow larger with time. This expansion was first hinted at in the early 20th century, when astronomers noticed that galaxies seemed to be moving away from us. Their light was red-shifted, meaning the wavelengths were stretched toward the red end of the spectrum. The farther away a galaxy was, the greater the redshift. Edwin Hubble measured this relationship and found that the velocity of recession increased with distance, a discovery that became known as Hubble's law. The simplest explanation was that space itself was expanding, carrying galaxies along like raisins embedded in rising dough. It's a common misconception that galaxies are receding from us because we occupy a special position, as though we sit near the centre of the universe and everything else is moving outward. In reality, the expansion looks the same from every vantage point. From any galaxy, anywhere, distant galaxies appear to be receding in all directions. It's not that everything is flying away from a central point, it's that every point in space is moving away from every other point as space stretches. There's no centre to this expansion, And there's no edge either. It's uniform everywhere, a property of space itself. To understand it more clearly, imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move farther apart, even though none of them are moving across the surface. The balloon's surface is stretching, and that stretching increases the distances between all points. From the perspective of any single dot, all the others appear to be receding. That's essentially what's happening in the universe, though the analogy isn't perfect, since the balloon's surface is two-dimensional, and the universe expands in 3 dimensions. But it gives a sense of how the distances between galaxies can grow, without galaxies themselves moving through space in the traditional sense. This concept of expansion has deep implications. It means the universe doesn't have a boundary that things move into. There's no outer shell, no wall, no outside. Instead, the universe is expanding everywhere at once, even empty space. The regions between galaxies where there's almost nothing is stretching. The rate of this expansion is described by the Hubble constant, a number that tells us how quickly 2 points in space drift apart for every unit of distance between them. The farther apart 2 galaxies are, the faster they recede. It's a proportional relationship built into the universe's geometry. But what's really being stretched? It's not matter, it's not energy. It's the underlying metric that defines how we measure distance. Spacetime itself, the 4-dimensional framework that combines space and time into a single fabric, is expanding. In Einstein's theory of general relativity, spacetime isn't static. It's dynamic, capable of bending, curving, stretching, and evolving depending on the mass and energy within it. When cosmologists solve Einstein's equations for a homogeneous isotropic universe, one that looks the same in every direction, they find that expansion or contraction is a natural outcome. The cosmos can't just sit still, it must change. In the early universe, the expansion was much faster, a rapid burst known as inflation. During inflation, space itself grew exponentially in an unimaginably brief instant, smoothing out irregularities and setting the stage for everything that followed. After inflation ended, the expansion slowed as gravity began pulling matter together, forming stars and galaxies. For billions of years, the expansion decelerated under the influence of that gravity. Then, more recently in cosmic history, something unexpected happened. The expansion began speeding up again. This acceleration was discovered in the late 1990s, when astronomers studying distant supernovae found that those exploding stars were dimmer than expected. That meant they were farther away than predicted by a steadily decelerating universe. Something was pushing galaxies apart faster than gravity could slow them. The name given to this mysterious driver is dark energy. We don't know what it is. We only know what it does. It causes the fabric of space to expand at an accelerating rate. The best current model of the universe, called the lambda CDM model, includes dark energy as a cosmological constant, a kind of built-in energy of empty space. The Greek letter lambda represents this constant in Einstein's equations. In this model, as space expands, the density of matter decreases, but the density of dark energy remains the same. That means that as the universe grows, dark energy becomes increasingly dominant. The more space there is, the more dark energy there is, and the faster the expansion proceeds. It's a feedback loop written into the structure of the cosmos. This realization has changed how we think about the universe's future. If dark energy remains constant, expansion will continue to accelerate. Galaxies not bound to ours will recede beyond visibility, their light stretched until it fades into the darkness. Over unimaginable spans of time, the observable universe will shrink in content. The Milky Way and its nearest neighbours will merge into a single massive galaxy, while everything beyond will vanish from sight. Eventually, distant galaxies will move away faster than light relative to us, their signals forever unreachable. The universe will appear increasingly empty, even though it's not truly ending, just expanding beyond our ability to see. This outcome, sometimes called the cosmic isolation, is one of the most sobering ideas in cosmology. It means that cosmic history is defined not only by what exists, but by what remains in contact. As space expands, communication between distant regions becomes impossible. Photons, particles, even information itself can't cross the growing gulf. The cosmic web of galaxies that now spans billions of light years will fragment into countless isolated islands, each surrounded by darkness. If any civilizations exist in these far-flung galaxies, they'll see the same fate unfold. Over time, their skies will empty too. Every observer, everywhere, will eventually live in a local pocket of stars, unaware of the vast universe that once surrounded them. It's important to remember, though, that expansion doesn't affect everything equally. On small scales, inside galaxies, within solar systems, within atoms, gravity and other forces are strong enough to resist it. The Earth doesn't drift away from the Sun. The atoms in your body don't stretch with the cosmos. Expansion only dominates on scales where gravity is too weak to hold things together. The universe expands between galaxies, not within them. That's why galaxies themselves remain intact, bound by their own gravity even as the distances between them increase. The idea that space can stretch, that distances can grow without motion through space, can feel deeply counterintuitive. We're used to thinking of space as a static backdrop where things happen, not as something that can change on its own. But general relativity teaches us that space and time are dynamic. They can warp around massive objects, creating gravity wells that bend light and alter time's flow. They can ripple, as in gravitational waves, and on the larger scales they can stretch, creating new space between distant points. One way to visualize it is to imagine a grid drawn on a flexible sheet. Each square represents a certain distance, and galaxies sit at the intersections. As the sheet stretches, the squares get larger. The galaxies don't move across the grid itself expands. The light travelling between them stretches too, increasing its wavelength. That's why the light from distant galaxies is red-shifted. Not because they're speeding through space, but because space itself has expanded while the light was en route. Every photon's wavelength is a record of how much the universe has stretched since it began its journey. When cosmologists measure that redshift, they're not just measuring motion, they're measuring the history of expansion. Each galaxy's light tells a story of how much the universe has grown since the light left. In that sense, telescopes are time machines. They don't just look outward, they look backward, reading the record written in stretched light. The expansion also means that the universe has no true center. Every point is moving away from every other point, and the geometry of space ensures that this is consistent everywhere. If you could somehow jump to a galaxy billions of light years away, you'd see the same pattern, everything else moving away from you. This uniformity, called isotropy, is one of the great pillars of cosmology. It means the universe has no privileged position, no cosmic center, and no outer edge. Wherever you are, you're at the center of your own observable universe, defined by how far light has travelled since the beginning. There's an elegance in this, even a kind of quiet reassurance. It means the universe looks the same from every location, not because we're special, but because the laws that govern it are. Every observer, no matter where they are, shares the same cosmic story written in expanding space. The distances may differ, the timescales may vary, but the physics is universal. Expansion also helps explain the cooling of the universe. When space stretches, it doesn't just carry galaxies apart, it stretches light itself, reducing its energy. That's why the cosmic microwave background has cooled from a brilliant orange glow to a faint microwave hum. Expansion spreads energy over a larger volume, diluting it. As the universe grows, its average temperature drops. In the far future, if expansion continues, it will approach absolute zero, a vast, dark cosmos filled with cold relics and thin radiation. Yet even in that quiet future, the expansion will go on. There's something serene in this picture. The universe doesn't expand violently. It stretches gradually, silently, invisibly, on scales beyond comprehension. You can't feel it, but it defines everything. Every moment, the space between distant galaxies grows larger. Every second, light travelling through that space stretches a little more. The expansion isn't a storm or an explosion. It's a slow unfolding. The geometry of the universe changing gently with time. As space stretches faster and faster, the most distant galaxies begin to disappear. They don't vanish all at once, and they're not slipping behind a curtain or falling off an edge. They fade gradually, their light growing fainter, redder, slower to reach us, until finally it cannot reach us at all. This quiet fading is one of the most haunting consequences of cosmic expansion. The universe doesn't just move outward, it carries parts of itself away beyond the reach of any observer. The galaxies we see tonight at the edge of detectability are already halfway gone, their light stretched nearly beyond recognition. By the time their next photons would arrive, the expansion will have carried them so far that those photons will never make it. The universe, in this way, has a built-in horizon of disappearance. Beyond a certain distance, galaxies recede faster than light, not because they're speeding through space, but because the space between us and them is expanding faster than light can cross it. There's no violation of relativity here, because the galaxies aren't moving through space at superluminal speeds. The space itself is stretching. And so, the light they emit can't bridge the growing gap. It's as though they're standing on the other side of a river, whose current grows stronger the farther you go, until even light cannot swim across. When we look deep into the cosmos, we're seeing not only what is far away, but what is nearly lost. Many of the faintest smudges of light detected by telescopes like Hubble or James Webb come from galaxies whose light began its journey billions of years ago, when the universe was young. Since then, those galaxies have moved tens of billions of light years farther due to expansion. The light that reaches us now is their ancient echo, the last signal that could ever make it here. Beyond that, they've drifted beyond communication, forever out of touch. To grasp what this means, imagine a future astronomer living perhaps 100 billion years from now. By then, dark energy will have continued to accelerate the universe's expansion. The Milky Way will likely have merged with its neighbouring galaxies, the Andromeda Galaxy and a few smaller companions, forming a single giant elliptical system. That future astronomer will look into the sky and see stars, perhaps the faint glow of surrounding clusters, but nothing beyond. The rest of the universe will have disappeared. The galaxies we see now, scattered across billions of light years, will no longer be visible. Their light, stretched by expansion, will have redshifted beyond detection, their last photons diluted into the darkness. This vanishing act isn't something that happens suddenly. It's gradual, like twilight fading into night. Over time, as expansion accelerates, the apparent brightness of distant galaxies declines exponentially. Even galaxies that remain technically within our observable universe, those whose light has reached us at least once, will eventually stop sending new light our way. Their most recent photons, emitted today, will never arrive. The universe we see is a memory in motion, always showing us the past, never the present, and constantly losing pieces of itself to the future. In a way, this cosmic erasure has already begun. Astronomers estimate that roughly 97% of all galaxies in the universe are already beyond our reach. They exist, they shine, they move, but their light will never reach us again. Only a small fraction, those relatively nearby, remain visible for the foreseeable future. The rest have crossed the threshold set by the speed of light and the expansion rate. They are still out there, but they are gone to us, not because of distance alone, but because the universe itself is outrunning its own messages. When you think of it this way, the universe we observe is like a shrinking island of memory surrounded by an expanding ocean of invisibility. Every passing moment, more galaxies drift beyond the horizon. Their light, already faint and ancient, stretches further until it fades into wavelengths so long that no detector could ever sense them. Over time, even the cosmic microwave background itself will redshift into radio waves too weak to register. The cosmos will remain vast, but our ability to perceive it will contract. The night sky, once filled with countless galaxies, will grow empty. This idea might sound melancholy, but it's simply the natural outcome of the universe's geometry. Expansion doesn't destroy the galaxies, it just removes them from causal contact. In physics, causal contact means the ability of 2 points to affect each other by any means, including light. When galaxies cross that boundary, no signal from us can ever reach them, and no signal from them can ever return. They become causally disconnected. The universe, as it expands, fragments into countless isolated regions, each cut off from the rest. Each one becomes its own pocket universe, self-contained and alone. What's fascinating is that this isn't some distant theoretical prediction. It's measurable. Astronomers can calculate which galaxies are already beyond the cosmic event horizon, meaning no future light from them will reach us. The dividing line sits around 16 billion light-years away. Anything farther is receding so quickly that new light emitted today will never arrive. We can still see them now, because we're catching the light they emitted long ago, but once that last light passes, they will fade permanently. The edge of visibility is constantly moving inward in practical terms, even as the universe expands outward. When cosmologists map the large-scale structure of the universe, the cosmic web, they see enormous filaments of galaxies separated by vast voids. The scale is almost incomprehensible. Each filament spans hundreds of millions of light-years, containing thousands of clusters, and yet, even this grand structure is temporary. Over time, gravity will draw the nearest galaxies together, forming superclusters, while expansion will stretch the spaces between those superclusters until they vanish from one another's view. The cosmic web will dissolve into isolated strands, each thread floating in its own expanding darkness. The galaxies that vanish beyond the horizon aren't lost entirely in the cosmic sense. They still exist, governed by the same physics, evolving in their own timelines. Their stars will burn out, their black holes will merge, their elements will form new worlds, but none of that will ever matter to us observationally. They are as real as anything we can see, but forever separated by a gulf of expanding space. The universe is vast enough that entire civilizations could rise and fall in those unreachable regions without any chance of detection. For all practical purposes, they might as well be in a separate universe. This gradual disconnection raises a strange philosophical point. When we talk about the universe, do we mean the part we can see, or the totality of everything that exists? The observable universe is defined by light, by what can reach us. But the universe itself, whatever that means in its entirety, might be infinitely larger, filled with regions we will never know. The vanishing galaxies are a reminder that the observable universe is not a fixed quantity. It changes with time, it's shaped by expansion, by the finite speed of light, and by our position in cosmic history. In the deep future, our observable universe will contain fewer and fewer galaxies, even as the actual universe grows larger and richer beyond our view. To put it another way, the universe doesn't grow empty. Our window into it grows smaller, the frame tightens, the picture fades. We are not witnessing the disappearance of existence, only the limits of our perception closing in as expansion outpaces communication. The information is still there, just unreachable. It's a humbling thought that reality continues beyond our knowing, indifferent to our ability to witness it. The light from those receding galaxies doesn't vanish instantly. It continues to travel toward us, stretched and cooled by expansion. As it shifts into longer wavelengths, it carries with it the story of what those galaxies once were. In that sense, we are surrounded by ghosts, signals from objects that no longer exist in the form we see them. When you look at a galaxy 13 billion light-years away, you're looking at a structure that may have changed completely, merged, evolved, or faded long ago. The image in your telescope is an ancient message, preserved in light. Each photon is a time capsule from an era when the universe was smaller, denser, and younger. That realization blurs the line between presence and absence. The galaxies we see on the edge of visibility are already beyond reach, and those beyond are already invisible. The universe, at any given moment, is both full and empty depending on how far you can look. What we perceive as the night sky is only a fragment of what exists, and that fragment is always changing. Astronomers sometimes describe this phenomenon as the cosmic horizon recession. As expansion continues, the horizon recedes from us, and with it, the ability to interact with the distant cosmos. The galaxies we can see today are closer to the horizon than they were yesterday, and the pace of that retreat accelerates. If you could somehow mark the edge of the observable universe and watch it over billions of years, you'd see galaxies slowly slip beyond it one by one, their light stretching to infinity before fading away. It's a process so slow and vast that no individual life or even civilization could notice it directly. But on cosmic timescales, it's inevitable. Even now, the most distant galaxies detected by the James Webb Space Telescope are relics from when the universe was less than 500 million years old. They're incredibly faint, their light stretched into infrared by expansion. To see them is to catch the last whispers from a time so far removed that it defies everyday language. Beyond them, there are certainly more galaxies, perhaps countless more, but they are already gone to us. Their light, though shining continuously, can never close the widening gap. Thinking about this doesn't have to feel bleak. In some ways, it highlights how precious the present moment of cosmic history is. We exist at a time when the universe is still readable, when the cosmic web is visible, when ancient light still reaches us. Future observers will not have that luxury. They will live in a smaller perceptual cosmos, their night skies quieter, their telescopes blind to the vastness we now see. The fact that we can look across billions of light years and trace the universe's evolution is a privilege of timing, a brief window before darkness closes in. This era, the age of visible galaxies, is temporary. It's a stage in the universe's story when light and expansion balance just enough to allow awareness of the whole. That awareness will fade, but the reality it once revealed will continue, indifferent and endless. The vanishing galaxies aren't dying so much as moving beyond the possibility of being known. They remain, silently expanding with space, part of a cosmos that continues to unfold. The more we learn about them, the clearer it becomes that the universe is not static, not eternal in its appearance. It changes slowly but profoundly, reshaping what can be seen and what can't. The galaxies drifting away now are not leaving us behind. They're following the same rules that govern everything. Expansion defines their destiny as it defines ours. The loss of visibility isn't the loss of connection in a deeper sense. It's simply the physics of an evolving cosmos. There is a place where the last visible light of the universe fades into silence. It isn't a line drawn across the sky, and it isn't a wall of any kind. It's a transition, gradual and invisible, a thinning of what can be known until it becomes indistinguishable from what cannot. Astronomers call this threshold the edge of the observable universe, but that phrase doesn't capture what it feels like to think about it. The silent borderlands are where time and distance combine to erase contact. It's where the light from the first galaxy stretches so thin that even our best instruments can no longer follow it. Beyond that, reality continues, but no information ever crosses back. These borderlands are the quietest regions of all, not because they are empty, but because they are beyond reach. The galaxies there still burn with stars, still rotate, still evolve, but their light will never again arrive. The expansion of space ensures it. At a certain distance, the outward stretching of the universe outpaces light itself. so the photons that set out toward us will never close the gap. To imagine that is to stand on the shore of an ocean that is forever receding, its surface always moving faster than any wave you could send across it. You can look out, but the view is frozen in the past. Everything beyond is sealed in silence. The silent borderlands aren't a region we could ever visit. If you could somehow travel at nearly the speed of light in any direction, you wouldn't reach them, because they aren't a place that stands still while you move toward it. The horizon retreats as you approach. It's not a destination, it's a property of time itself. Every observer in the universe carries their own horizon, centered on their position, marking the limit of what can ever be seen or influenced. It moves with you, grows with you, and defines the edge of your visible reality. When you look at deep field images taken by the James Webb or Hubble telescopes, you're looking into those borderlands. Every faint red smudge, every distant speck is a message from a galaxy so far away that its light left billions of years ago when the universe was still young. The light that reaches us now began its journey before the Earth existed, before the Sun was born, before the Milky Way had even taken shape. It's easy to forget looking at such images that you're not seeing those galaxies as they are now. You're seeing them as they were in their infancy, their ancient light stretched and dimmed by time and expansion. If you could somehow see them today, they would be far beyond where your eyes could follow. At those distances, light behaves differently. It isn't just faint, it's distorted. The wavelengths are stretched by cosmic expansion until they move beyond visible colours and into infrared, then microwave, and eventually into radio frequencies so low they can no longer be detected. The galaxies themselves continue to shine, but their light is pulled away from us, its energy diluted by the stretching of space. The photons that left them billions of years ago are still travelling, but they'll never arrive. They are trapped in a universe that expands faster than their own motion can overcome. You could think of it as the universe's natural boundary between communication and isolation. Within this boundary, light and gravity and information can travel freely, connecting distant parts of the cosmos. Beyond it, causality breaks down. No signal, no force, no influence can cross from one side to the other. It's not a barrier you could touch. It's an event horizon, an invisible surface defined by what can never return. The same kind of horizon exists around black holes, where gravity is so strong that light cannot escape. The difference is that the cosmic event horizon isn't created by gravity, but by expansion itself. Space isn't pulling things in, it's carrying them away. From our point of view, this horizon lies about 16 billion light-years away, depending on how you define it. Everything beyond that distance is already out of contact. Galaxies farther than that still emit light, but the universe's expansion ensures that light will never reach us. The photons they send now are like messages written on water, erased by the flow before they can reach the other side. That makes the silent borderlands a kind of cosmic no man's land, filled with galaxies, yet cut off from every observer forever. Even though it's invisible, we can infer its presence. The patterns in the cosmic microwave background tell us how the universe expanded over time. By comparing those patterns to the distribution of galaxies we can see, astronomers can calculate where the horizon lies. It isn't static. It changes as the expansion accelerates. Over time, more regions slip beyond it, and the borderlands move closer to us. The observable universe becomes a shrinking bubble of communication in an ever-growing sea of isolation. For now, though, we still receive light from near that edge. The most distant galaxies detected so far appear as faint red smears in telescope images, their photons stretched nearly to invisibility. They represent the frontier of what's possible to observe. Each one is a relic from when the universe was only a few 100 million years old. To look at them is to see the dawn of structure, the first clumps of gas collapsing into stars, the first galaxies taking shape. Beyond them, there are certainly more galaxies, perhaps an infinite continuation of them, but they are already in silence. What's remarkable is how consistent the view is in every direction. These silent borderlands surround us evenly, forming a spherical horizon centered wherever you stand. If you move to another galaxy, the horizon would move with you. Every observer, everywhere, has their own bubble of visibility. That symmetry is one of the great clues to the universe's structure. It tells us that space itself expands uniformly, without a center or an edge. There's no special place from which expansion radiates. It happens everywhere at once. The silent borderlands aren't at the edge of the universe, they're the edge of perception. It's strange to think that beyond that horizon, events are still unfolding. Stars are being born and dying. Galaxies are colliding and merging. Light is being emitted constantly, but none of it will ever reach us. To us, those events are in permanent shadow. They belong to a region of space-time that is forever disconnected. In that sense, the universe contains infinitely more than we will ever know. Most of its volume lies beyond communication, beyond discovery, beyond sight. We live in a small, privileged bubble of awareness, surrounded by a vast silence. This isn't silence in the way of emptiness. It's silence in the sense that no message can cross it. The borderlands are not devoid of matter or energy. They are full of galaxies, radiation, and perhaps even life. But they exist in a separate timeline from ours. Their past and future cannot interact with our own. The expansion of the universe has divided reality into regions that can never influence each other again. To them, we are equally unreachable, invisible, already gone. Thinking about this can give you a sense of perspective unlike anything else. It suggests that reality is larger than any story we can tell about it. The observable universe, vast as it is, might be just one region among countless others, each with its own silent borderlands. It's not that there's a physical boundary keeping them apart, but that time and expansion themselves enforce the separation. Space-time is not infinite in what it connects. It's infinite in what it isolates. Yet even in this separation, there's continuity. The laws of physics don't stop at the horizon. Whatever happens beyond it still follows the same rules. The same particles, the same forces, the same constants continue to operate. The difference is that we can never test or observe them directly. These silent borderlands mark the end of observation, not the end of reality. They are a mirror to our limits, showing us how far knowledge can reach before it gives way to wonder. Sometimes, cosmologists describe the universe beyond the horizon as being forever out of causal contact. It's a technical phrase, but it carries a kind of quiet poetry. It means that the web of cause and effect that connect everything we know doesn't extend past that line. No light, no gravity, no signal of any kind can bridge the distance. The borderlands are where causality dissolves into possibility. They are where the known universe stops being a single connected whole and becomes an endless collection of disconnected regions, each with its own destiny. In that sense, the silent borderlands are both boundary and bridge. They connect what we can see to what we can only imagine. They remind us that our view of the universe is temporary and local, defined by the physics of expansion and the passage of time. They also remind us that beyond our reach lies a continuation, a larger story we'll never witness but that still exists. The galaxies beyond the horizon don't vanish from existence, they vanish from relevance to us, and yet their existence still shapes the universe's overall geometry. Even what we can't see leaves an imprint on what we can. When astronomers calculate the total density of matter and energy, they have to include the unseen. The gravity of distant, unreachable regions still affects the curvature of space-time as a whole. The universe's shape depends on all of it, seen and unseen alike. In that way, the silent borderlands are part of the same structure that holds everything together. They're not a separation in nature, only in knowledge. The universe doesn't divide itself. We divide it by what we can measure. It's possible that the borderlands also hide transitions in the physics we know. If the universe is infinite, then beyond our horizon there could be regions with different structures, different arrangements of galaxies, perhaps even slightly different conditions set by quantum fluctuations in the early universe. Inflation theory suggests that space could be vastly larger than our observable portion, perhaps containing variations that we'll never detect. If that's true, then the silent borderlands are not just the end of sight, they're the edge of diversity in cosmic structure. Beyond them might lie regions so different that, from our perspective, they might as well be other universes. Whether those regions exist or not, the principle remains. The universe extends beyond what can ever be known. The silent borderlands aren't an anomaly, they are the rule. The part we can see is the exception, a small, illuminated patch in an otherwise unobservable whole. That realization has changed how scientists think about cosmology. The goal isn't to describe the entire universe, because that's impossible. The goal is to describe the observable part well enough to infer what might lie beyond, using mathematics, logic, and the faint traces left by expansion. In the end, the silent borderlands are both the limit and the invitation. They are where science meets its horizon, and where curiosity continues without end. To stand at that boundary in thought is to accept that not everything can be known, but that everything can still be wondered about. The light that fades there doesn't mark an ending. It marks the beginning of the invisible. If the universe fades into silence beyond what we can see, what could be out there? Is it more of the same, galaxies and matter continuing forever? Or is there something else? A realm shaped by inflation, by quantum chance, or by something we haven't yet imagined? Beyond the horizon's faint glow lies a place we can never see, yet one that logic insists must exist. It isn't a realm of fantasy, and it isn't a void. It's the continuation of everything, a region where the same laws of physics still apply but where observation fails. When we talk about what lies beyond the observable universe, we're talking about parts of the cosmos that haven't had time to share light with us since the beginning. The horizon marks not a limit of existence, but a limit of communication. Past that threshold, the universe continues as surely as the ocean continues, beyond the edge of sight from a ship's deck. To imagine what might lie beyond that glow, we start with what we know. Every direction we look, the universe appears uniform on large scales. The distribution of galaxies, the patterns in the cosmic microwave background, the temperature of the ancient light, all of it points to a cosmos that looks much the same everywhere. This uniformity implies that the regions we can't see are probably similar to the ones we can. There's no reason to think the universe suddenly changes character right at the point where light stops reaching us. The physics doesn't stop there, the expansion doesn't stop there. It's simply that time and distance have conspired to hide the rest. So, in the most straightforward sense, beyond the observable universe lies more universe, more galaxies, more clusters, more dark matter, and more dark energy stretching the fabric of space. The part we can see is just a fraction of the whole. If the universe is infinite, then our observable region is like a single patch on an endless quilt. If it's finite but unbounded, like the surface of a sphere, then the horizon merely loops back on itself in ways we can't detect. Either way, the universe extends beyond the reach of our senses. The question isn't whether there's something beyond, but what form that continuation takes. Cosmologists have tried to approach this question carefully, using evidence that can be tested indirectly. The most powerful clue comes from the cosmic microwave background. The patterns of temperature and density fluctuations in that ancient light tell us about the geometry of space. When researchers analyse those patterns, they find that space is flat to within a tiny margin of error. If it were curved positively, like the surface of a sphere, the light from distant regions would converge slightly, creating distinctive patterns. If it were curved negatively, like a saddle, the light would diverge. But the measurements show no such curvature on observable scales. Flatness implies that if the universe curves at all, it does so on scales much larger than what we can see. That suggests an expanse beyond the horizon far greater than our visible portion, potentially infinite. Infinity is a difficult concept to handle. Even in physics, it's not just big, it's without boundary, without repetition in any direction. If the universe is infinite, then the region we observe is just one infinitesimal part of an unending continuum. Somewhere, unimaginably far beyond our horizon, there could be other galaxies almost identical to ours, other stars, other planets, and perhaps even other versions of ourselves. Not because of anything mystical, but because infinity allows every arrangement of matter to occur somewhere. Given enough volume, even the improbable becomes inevitable. The same physical laws acting on an infinite canvas can paint endless variations. Of course, we can't verify any of that. It's speculation guided by logic and mathematics, not observation. We can infer what's likely, but we can't confirm what's real beyond the horizon's glow. Still, the evidence we do have supports the idea of continuity. Nothing in the cosmic data suggests an edge, a boundary, or a transition. Every measurement points to smoothness, to sameness on large scales. It's reasonable then to think that beyond what we can see lies more of what we already know. More stars forming, more galaxies spinning, more light travelling endlessly into the dark. But there are other, stranger possibilities. The smoothness of the universe doesn't necessarily mean uniformity everywhere. Inflation theory, our best explanation for how the universe expanded from its earliest moments, suggests that space might be far larger than we can observe, possibly composed of many distinct regions with different properties. During inflation, the universe expanded exponentially, faster than light, smoothing out irregularities and creating vast regions of space-time that were never in contact with each other. Inflation may not have ended everywhere at once. In some areas, it could have continued indefinitely, producing new pockets of space, new universes, while our own region cooled and slowed. If that's true, then beyond the horizon might not be just more of the same universe, but other universes altogether, each with its own conditions. Some might have slightly different laws of physics, different particle masses, different forces, different constants. Others might be entirely unrecognizable. Together, these regions form what physicists call the multiverse, a vast and possibly infinite collection of universes born from the same cosmic process. We can't see them, and we may never detect them, but the mathematics of inflation makes their existence plausible. The silent borderlands could be just one of countless transitions between visible and invisible realms. It's worth remembering that this idea doesn't come from imagination alone. It arises naturally from equations describing inflation and quantum fields. When the early universe expanded rapidly, quantum fluctuations, tiny variations in energy, were stretched to cosmic scales. Those fluctuations seeded the galaxies we see today. But in some regions, inflation might have lasted a little longer, allowing new pockets of space to bud off. This process, known as eternal inflation, creates an infinite mosaic of bubble universes, each with its own physical constants and histories. We inhabit one of those bubbles, and beyond our horizon could lie others, forever unreachable. If that picture is correct, then the horizon's glow is not the edge of our universe, but the surface of our local bubble, surrounded by others expanding beyond contact. The observable cosmos becomes a small patch in an immense foam of universes. Each bubble's interior follows the same fundamental laws, but their details may differ. It's an unsettling vision, because it replaces the idea of a single universe with an endless ensemble, each isolated from the rest. Yet it's also consistent with what we know, that space-time can stretch indefinitely, and that quantum fluctuations can give rise to new regions. Even if we set aside the multiverse, the idea of continuation remains. Beyond the horizon, the same cosmic expansion continues to shape regions we'll never see. Those regions are not static. They have their own histories, their own future horizons, their own silent borderlands. The universe doesn't stop existing just because light can't cross from there to here. It simply continues, carrying on without us, indifferent to whether it's observed. Sometimes people ask what it would mean to travel beyond the horizon. Could a spacecraft, given enough time, cross that boundary and see what lies beyond? The answer is no, not because of any physical barrier, but because the horizon isn't a place. It's defined by light and time. If you travelled outward, the horizon would move with you, always receding, always staying the same distance ahead. You'd never reach it, because it's not fixed. It's the limit of how far information can travel, and that limit expands as you move. The horizon exists relative to every observer, a boundary that always surrounds but never meets you. In a way, this makes the universe feel both intimate and unreachable. Everywhere you go, you're at the center of your own visible sphere, surrounded by light from all directions, fading toward the horizon. The cosmos appears centered on you, but it's not personal. Every observer, everywhere, experiences the same symmetry. The horizon's glow encircles them too, marking the boundary of what they can know. The universe ensures that everyone lives within their own private bubble of visibility, each bounded by light's finite speed and expansion's relentless pull. That thought leads naturally to another question. If there are infinite regions beyond our horizon, does that make our place insignificant? The scale might suggest so, but the answer depends on how you define significance. The immensity of what lies beyond doesn't erase what exists within. It simply places it in context. Our patch of the universe is small, but it's complete in itself. It contains everything that can ever influence or be influenced by us. From our perspective, it is the entire cosmos. Beyond the horizon's glow, the universe continues, but it will never touch us again. Its existence is real, but its story will never merge with ours. There's something profoundly stable in that idea. It means the universe is self-consistent. Every observer sees a complete cosmos, even though those cosmoses overlap only partly. Reality doesn't need to be seen in full to exist in full. It unfolds independently of perception. Beyond the glow lies continuity, not emptiness, a reassurance that existence doesn't depend on awareness. If you think of it that way, the horizon's glow is like the faint light of evening on the edge of vision. You can't follow it into the dark, but you know the world continues there. You can feel its persistence in the quiet of space, in the steady expansion that carries everything forward. The regions beyond might be unreachable, but they are not irrelevant. They define the boundary conditions that shape our own observable universe. The flatness of space, the smoothness of background radiation, the uniformity of cosmic structure, all of it depends on what lies beyond. Even though we can never see past that glow, the mathematics of cosmology lets us trace its influence. When scientists model the universe, they must account for everything, including the unobservable. The curvature of space, the rate of expansion, the behavior of dark energy, all depend on what happens beyond the visible. In that sense, the unseen still shapes the seen. The universe is continuous, even if our experience of it isn't. It's also possible that the boundary between what we can and can't observe changes over time in ways we don't yet fully understand. As dark energy accelerates expansion, the horizon of the visible universe shifts. Some regions move out of reach, while others that were once hidden may come briefly into view due to the curvature of space-time. The geometry is complex, but the principle remains. What we can see is only a fraction of what there is, and that fraction is always evolving. When you look at the night sky, every star and galaxy you see is a reminder that light has bridged unimaginable distances to reach you. Beyond the visible stars lies an ocean of others whose light will never arrive. The faint glow of the horizon is the dividing line between what light has already accomplished and what it never will. It's the edge of the universe's conversation with itself, the last visible whisper of the infinite. and as expansion continues to carry galaxies outward, we are left with a deeper curiosity. If space can stretch endlessly, if there are perhaps infinite regions beyond the glow, then what began it all? What caused the expansion to start, and what determines its speed, its smoothness, its endurance? In the earliest moments after the beginning, the universe did something extraordinary. It didn't just expand, it surged. It grew faster than light, faster than thought, faster than the language we have to describe motion. It didn't explode into space. It created space itself at a rate so immense that distances between points grew from subatomic to astronomical in a fraction of a second. This phase is called inflation, and it may be the reason the universe looks the way it does now, flat, smooth, and vast beyond comprehension. Inflation isn't just a metaphor for rapid growth, it's a literal description of space stretching exponentially. Imagine the universe smaller than a grain of sand, yet containing all the energy that would one day become every galaxy, every atom, every photon. Then, for reasons still partly hidden, that energy caused space itself to balloon outward by an inconceivable factor, perhaps by 100 orders of magnitude, in less than a trillionth of a second. To put that in context, it's as though something the size of a proton expanded to the size of the observable universe, almost instantly. The expansion wasn't an explosion pushing matter outward into emptiness. It was the creation of new space everywhere, all at once. Before inflation was proposed, cosmologists faced several puzzles. One was the horizon problem. The cosmic microwave background, the afterglow of the Big Bang, shows the universe was remarkably uniform in temperature across vast distances, but those distant regions are so far apart that light could never have travelled between them to even out their temperatures, not in the time since the Big Bang. How could parts of the universe that never touched each other end up so similar? Inflation provides the answer. Before expansion, all those regions were once close together, able to exchange energy and reach equilibrium. Then inflation stretched them apart so quickly that they became distant, yet still carried the same conditions imprinted from their shared origin. Another puzzle was the flatness problem. Observations show that space is extremely flat, not curved like a sphere or saddle, but geometrically balanced. Maintaining that flatness over billions of years requires incredibly precise initial conditions. Even a tiny deviation at the beginning would have grown over time, producing a universe either too curved to expand or too open to form galaxies. Inflation naturally explains this too. Just as the surface of a balloon looks flatter as it inflates, the rapid expansion smoothed out any initial curvature, leaving space flat over observable scales. A third puzzle was the problem of unwanted relics. Some early models of particle physics predicted heavy exotic particles that could have filled the universe in destructive abundance. Inflation would have diluted them, stretching their density so thin that they became negligible. It's a cosmic reset button, ironing out irregularities and leaving behind a universe ready to cool, form matter, and begin the long process of evolution. The mechanism behind inflation involves a hypothetical field called the inflaten. In physics, fields are invisible entities that fill space and can store energy. The inflaten field would have been in a high-energy state, pushing space to expand. When the field decayed to a lower energy state, inflation ended, releasing its energy into a burst of particles and radiation. The event we recognise as the Big Bang's aftermath. In that sense, the Big Bang wasn't the beginning of everything, but the end of inflation's burst. Space was already there, filled with energy, expanding faster than light, and when inflation stopped, that energy transformed into the matter and radiation that built the universe we now see. What makes inflation compelling is how well it fits the data. The tiny ripples seen in the cosmic microwave background, the small variations in temperature across the sky, match precisely what inflation predicts. Quantum fluctuations in the inflaten field, magnified by expansion, became the seeds of galaxies and clusters, Random jitters on microscopic scales were stretched to cosmic proportions, leaving an imprint that would later guide the formation of structure. Without inflation, those fluctuations would have been too small or too uneven to produce the universe we inhabit. But inflation's implications go far beyond explaining smoothness and flatness. It suggests that the universe we see might be only one pocket of a much larger and possibly infinite structure. The mathematics of inflation doesn't require the process to stop everywhere at once. In fact, under most versions of the theory, it continues indefinitely in some regions. This means that while inflation ended here, allowing our universe to cool and form stars, it may still be ongoing elsewhere, spawning new regions of space, new universes, each with its own properties. This idea is called eternal inflation. In this picture, space is like a vast field in which inflation continues to occur in different patches. Some regions stop inflating and form bubble universes like ours. Others continue expanding. The bubbles never meet because the space between them keeps growing faster than they can collide. Each bubble becomes an isolated cosmos, potentially infinite within itself, surrounded by a sea of inflating space. If this model is correct, then our universe is just one bubble in a cosmic foam without end. In some of those other bubbles, the laws of physics could differ. The values of fundamental constants, the strengths of forces, even the number of spatial dimensions might vary slightly. These differences arise from quantum fluctuations during inflation, which could set different initial conditions in each region. Some bubbles might produce long-lived universes like ours. Others might collapse quickly or remain sterile, never forming complex structures. From the perspective of physics, every possibility allowed by the equations could occur somewhere. Inflation doesn't just create space, it creates variety. To imagine eternal inflation is to confront scale in a way that defies intuition. Our observable universe, spanning 93 billion light-years across, would be a microscopic point in the larger inflating space. Beyond our horizon, other regions could stretch infinitely, each with its own galaxies and histories. The total structure might be infinite in every direction, filled with countless universes forming endlessly. And because the process never stops, it ensures that there will always be new regions, new beginnings, new possibilities. It's a concept both exhilarating and disorienting. On one hand, it solves many problems. It explains why our universe appears so uniform and flat, why it contains the patterns we see in ancient light, and why its structure fits the mathematical predictions of general relativity and quantum mechanics. On the other hand, it opens questions we may never answer. If inflation is eternal, how could we ever know what lies beyond our own bubble? Every attempt to observe outside fails by definition. The expansion is faster than any signal can travel, and the boundaries between bubbles are unreachable. The evidence for other universes may remain forever indirect. Still, physicists can look for traces of inflation's earliest moments. If two bubble universes ever came close enough to interact before drifting apart, they might leave faint signatures in the cosmic microwave background. Tiny circular patterns or anomalies in the temperature map. So far, none have been confirmed, but the search continues. Other tests focus on gravitational waves. Inflation would have produced a background of primordial ripples in space-time, which could leave subtle imprints on the polarization of the cosmic microwave background. Detecting those would provide powerful evidence for inflation's reality. Experiments in Antarctica and space are already searching for them. Even if direct proof of eternal inflation remains elusive, its logic is hard to dismiss. The equations describing inflation don't contain a natural stopping mechanism. Once it begins, it keeps going somewhere, always producing more space. From a mathematical standpoint, inflation doesn't just describe how our universe began. It describes a process that never ends. It's creation written into the geometry of reality. If that's true, then infinite possibility isn't just a philosophical idea, it's a physical one. Every potential configuration of matter and energy that could exist might exist somewhere within the inflating cosmos. The range of variation is unimaginable, but the principle is simple. Given infinite space and time, everything that can happen will happen endlessly, without repetition, yet without conclusion. Our own universe becomes one expression among countless others. Some scientists find this idea deeply unsatisfying because it seems to move beyond testable science. If we can never observe these other universes, can the theory be called scientific? Others argue that the logic of physics compels it. Inflation explains the data we can see, and its natural consequence is continuation beyond what we can measure. Whether or not we can ever test those outer regions doesn't change the fact that they follow from the same mathematics that successfully predicts our own. What eternal inflation really shows is that the universe may have no single beginning or end. Each bubble universe begins with its own version of a big bang, emerging from the inflating background, expanding, cooling, and evolving independently. New universes form as old ones age. There is no centre, no overall timeline, just a self-generating process continuing forever. In such a framework, the phrase the universe becomes less about one thing, and more about a collection of things, each with its own internal story. If you step back from the theory and think about it in everyday terms, it means that what we call everything might not be everything at all. Beyond the horizon's glow could lie an infinite landscape of other realities, all following the same fundamental logic but diverging in details. Some might be empty, some might teem with galaxies, some might last only seconds. Ours happens to be one where the conditions allow matter, stars, planets, and observers to exist long enough to wonder about them. And yet, even if infinite possibility is real, it doesn't change the immediacy of the universe we inhabit. The physics that governs our world is complete and consistent within its own bubble. The light we see, the galaxies we map, the particles we study, all belong to this self-contained region of space-time. We don't need to see beyond it to understand that it's part of something larger. Just knowing that it might continue beyond the horizon gives context to everything we can measure. It tells us that our visible universe is part of a broader continuum, a single patch in an endless expansion that began with inflation and continues still. When cosmologists describe this, they do so with precision rather than wonder, but the wonder is there nonetheless. It lies in the fact that we can trace the story back so far, from the structure of galaxies to the patterns in ancient light, to the behaviour of quantum fields in the universe's first instant. Inflation connects the smallest and the largest scales in existence, linking subatomic uncertainty to cosmic structure. It shows that every star, every atom, every person is the result of fluctuations that began in an era when space itself was smaller than a proton. That connection between quantum randomness and cosmic order might be the most profound part of all. It means that the vast structures we see in the sky, the galaxies and clusters spanning billions of light years, grew from tiny fluctuations in energy fields during inflation. The seeds of everything were quantum. The universe's grandest forms began as microscopic uncertainty, magnified by expansion. In that sense, infinity itself may have emerged from something smaller than comprehension. And while inflation explains how the universe became so large and uniform, it also leads to another question. What happens when those inflating regions keep producing new universes? What does that infinite process look like from within one of its creations? If you could step outside of the universe, beyond even the edge of what can be seen, what would you find? Not an edge like the walls of a room, but an infinite continuation, an expanse beyond imagining, where every possible universe is born from a process that stretches endlessly into space and time. This idea, while strange, is at the core of a theory called eternal inflation. And at the heart of this idea is the notion of bubble universes, separate realms of space-time, each with its own laws and characteristics, arising from an ever-expanding cosmic foam. Imagine the universe as a vast, frothy sea, and within it, bubbles of space-time are constantly forming. These bubbles are universes, each one expanding, cooling and evolving according to its own rules. The space between these bubbles is growing, but within each bubble the laws of physics remain consistent. The stars burn, galaxies form, and time flows in much the same way as it does in our own universe. But each bubble is isolated, separated by a vast, unbreachable gulf. It's as though the universe is constantly giving birth to new pockets of reality, each one expanding into its own infinite horizon. The concept of bubble universes comes directly from the idea of inflation. When inflation first occurred in the early moments of the universe, space itself expanded exponentially, causing tiny fluctuations in the energy field. Some of these fluctuations didn't stop when inflation ended. Instead, they kept inflating, forming distinct regions where space itself continued to expand at a rapid pace. These regions are the bubble universes. Each one forms from a quantum fluctuation, and each one has the potential to develop into a self-contained cosmos. In a sense, you could think of inflation as a cosmic factory, producing an endless array of these bubbles. Some bubbles may form and expand into regions that are just like our universe. Others might end in a cold, empty vacuum with no stars or galaxies. Some could have different physical constants, altering the behavior of light, gravity, and matter. The possibilities are endless, and each bubble represents an entirely different version of reality born from the same fundamental process. One of the most fascinating aspects of this idea is that the bubbles can never interact with one another. Once a bubble universe is created, it is isolated. The space between bubbles expands too rapidly for them to come into contact. There's no way for information, light, or matter to travel between them. Each universe becomes an independent island in the sea of eternal inflation. To us, the other universes are not just distant, they're unreachable, forever cut off by the fast expanding space between them. Even though we can never directly observe other bubbles, their existence may still be inferred through the effects they have on our own universe. Some cosmologists speculate that the collision of bubbles could leave traces in the cosmic microwave background, the ancient light left over from the Big Bang. If two universes came close enough to collide, they might produce subtle distortions in the fabric of space-time, ripples that could be detected. These bubble collisions are theoretical, but the idea is compelling. If such distortions exist, they could be the first direct evidence of the existence of other universes. For now, however, our best evidence for bubble universes comes from the mathematics of inflation. The theory of eternal inflation, which drives the production of bubble universes, is consistent with the data we see in the cosmic microwave background. The tiny fluctuations in temperature across the sky, those faint ripples in the background radiation, are thought to be the remnants of quantum fluctuations that occurred during inflation. These fluctuations didn't just create galaxies and clusters of galaxies, they also seeded the formation of bubbles. Each one could be the birthplace of a new, self-contained universe. Eternal inflation doesn't just explain the large-scale uniformity of the cosmos, it also opens the door to an entire multiverse, an infinite number of universes, each with its own history, its own set of rules, and its own potential for life. In the context of the multiverse, the universe we live in becomes just one of many, each one as real as the next, but forever beyond our ability to reach. The idea of a multiverse is both exhilarating and unsettling, suggesting that our understanding of the universe is limited by our perspective, and that the true scale of reality is far greater than we can imagine. One of the most compelling reasons to consider bubble universes is that they provide a natural explanation for why our universe seems so well tuned for life. In the standard model of cosmology, the constants of nature, such as the strength of gravity, the electromagnetic force, and the masses of elementary particles, are finely balanced to allow galaxies, stars, planets, and life to form. If any of these constants were slightly different, life as we know it wouldn't exist. The fine-tuning problem has puzzled cosmologists for decades. But if there are infinite bubble universes, each with its own set of physical laws, then it's not surprising that our universe happens to have the right conditions for life. It's simply one of many universes where the constants fall within the narrow range that allows complexity to emerge. In other bubbles, life may not be possible, but in our bubble, it is. And that's just one of the countless variations that inflation produces. If the idea of multiple independent bubbles forming across an infinite expanse sounds strange, it's because it challenges the very concept of a universe. Traditionally, a universe is something unified and contained, something that you can measure, study, and understand. But eternal inflation tells us that the universe, in a way, is not a single entity at all. It's a dynamic, ongoing process of bubble creation, with new universes emerging from the inflationary field at all times. The universe we live in is just one of those bubbles surrounded by an infinite sea of others, and while we can study our bubble in detail, we can never study the others. They remain forever out of reach, like islands lost in an endless ocean. This concept challenges our understanding of space itself. In our everyday experience, space is something static, something we move through. We imagine it as a stage where events unfold. But inflation and eternal inflation show us that space is not a passive backdrop. It is an active participant in the universe's evolution. Space expands, stretches, and creates itself. It's a process that continues without end, creating new regions of space, new possibilities, and new realities at an ever-accelerating rate. The fabric of space is alive with potential, each fluctuation in the energy field giving rise to a new possibility, a new bubble, a new universe. To picture the vastness of this process, imagine that the fabric of the universe is made of threads, and each thread represents a different bubble universe. The threads weave in and out of each other, crossing, diverging, and stretching, but they never meet. Each bubble expands at its own pace, creating new space around it, and each universe lives in isolation from the others. The space between these threads grows, ensuring that no two universes can ever interact. But within each universe, the story unfolds. Stars burn, galaxies collide, and life evolves, all according to the physical laws that govern that particular bubble. It's an unsettling thought, to think that the universe we know is just one thread in an infinite web. But it's also a humbling one. It suggests that the universe is not as special as we once thought. It's just one manifestation of a process that continues forever, creating new universes, new possibilities, and new realities. The universe is vast, not because it's big in the way we understand, but because it's infinite in its potential for variation. Eternal inflation and the idea of bubble universes provide a framework for thinking about the vastness of space in a way that our traditional models cannot. It's not just about how big the universe is or how far the stars extend. It's about the fact that space itself is creating new space, and that each new pocket of space, each bubble, is a universe unto itself, complete with its own history, its own structure, and its own potential for life. Of course, we'll never be able to observe other bubbles. Our bubble, our universe, is all we will ever know. The space between bubbles is expanding too quickly for light, gravity, or any signal to cross it. Each bubble is a self-contained cosmos, isolated by the very expansion that brought it into being. But that doesn't make the other bubbles any less real. It just means that the scope of our knowledge is limited to the small corner of the cosmic foam in which we reside. If the multiverse is real, then the universe we see, our observable cosmos, is only a fraction of the full story. The idea of infinite bubbles doesn't just expand our view of space, it shifts our understanding of what it means to exist in the first place. Our universe may be just one of countless others, each one with its own rules, its own possibilities, and its own future. We are part of a vast ongoing process that creates new realities continuously. This idea also reshapes our concept of time. If eternal inflation is occurring, new universes are being born continuously, with each one evolving at its own pace. Our universe is just one chapter in an infinite book, a single passage in an endless cycle of creation. Time, in this sense, doesn't have a final destination. It's not a story that begins with the Big Bang and ends with the heat death of the universe. Instead, it's an ongoing process that repeats across infinite bubbles, each universe a new expression of spacetime, expanding endlessly. This understanding of the universe as an ever-creating, ever-expanding cosmic foam changes everything. The universe isn't static. It's a dynamic process of creation, where new bubbles of spacetime emerge constantly. The reality we know is just one of those bubbles, and we are part of an eternal expansion that will continue long after we're gone. The universe is more vast and more mysterious than we can ever fully understand, not because it's simply large, but because it is constantly becoming. If inflation set the universe in motion, then dark energy is what keeps it moving. Long after the first galaxies formed, after the stars ignited and began to fill space with light, something quiet began to change in the fabric of the cosmos. The expansion, which had been slowing under the pull of gravity, began to speed up again. It was as if the universe took a deep breath after billions of years and started to stretch faster than before. This acceleration, first discovered near the end of the 20th century, revealed that the universe's story wasn't one of slowing and collapsing, but of unending growth. The cause of that acceleration is what we call dark energy, a name that explains nothing and hides everything, because it's less a thing than a property of space itself. For decades, cosmologists believed the expansion of the universe would eventually slow down. The logic was simple. The galaxies all exert gravity on one another, and gravity pulls things together. Even if the universe began with tremendous outward momentum, that pull should gradually counteract it. Depending on how much matter the universe contained, it might slow forever, or it might stop expanding and reverse into a collapse, a big crunch. That view held for most of the 20th century, until astronomers began studying distant supernovae. Type Ia supernovae are special. They're the explosions of white dwarf stars that have accumulated too much material from a companion. When they reach a critical mass, they detonate with nearly identical brightness every time, making them useful as standard candles. By comparing how bright they appear to how bright they should be, astronomers can calculate their distance. When researchers measured supernovae in faraway galaxies, they expected to find evidence of deceleration. Instead, they found the opposite. The supernovae were dimmer than expected, meaning they were farther away than they should have been if the universe's expansion was slowing. The conclusion was inescapable. The universe was expanding faster and faster. That discovery, announced in 1998, changed cosmology overnight. Something unknown was overpowering gravity on the larger scales, pushing galaxies apart at an accelerating rate. Whatever it wasn't matter, because matter attracts. It wasn't radiation, because radiation thins out as the universe expands. The simplest explanation was that empty space itself had energy, a constant, uniform energy that didn't dilute with expansion. This energy acts as a kind of anti-gravity, repelling rather than attracting, and as space grows, the effect grows with it. Einstein had predicted something similar decades earlier, though for different reasons. When he formulated general relativity, he found that his equations allowed for a dynamic universe, one that could expand or contract. But at the time, astronomers believed the universe was static. To keep it from collapsing under its own gravity, Einstein added a term to his equations, the cosmological constant, a kind of energy that would balance gravity and hold the universe steady. Later, when Hubble discovered that galaxies were receding from one another, Einstein abandoned the constant, calling it his greatest blunder. Ironically, it turned out to be right. The cosmological constant describes exactly the kind of energy that now seems to dominate the universe. In modern terms, the cosmological constant is the simplest form of dark energy, a fixed energy density inherent to space itself. Unlike matter, whose density decreases as the universe expands, the energy of the vacuum remains constant per unit volume. That means that as the universe grows, there's more space, and therefore more dark energy. It's this self-reinforcing property that drives acceleration. The more the universe expands, the more dark energy there is, and the faster the expansion continues. At present, dark energy makes up roughly 70% of the total energy content of the universe. Dark matter contributes about 25%, and ordinary matter, the kind that forms stars, planets, and people, makes up less than 5%. That means most of what exists is something we don't understand. We can measure its effects, but we can't detect it directly. It doesn't emit light or interact with matter except through gravity. It's invisible, but it shapes the destiny of everything. To understand how it works, imagine a universe filled with galaxies bound together by gravity. As expansion continues, galaxies move farther apart and their mutual gravitational pull weakens. If only gravity acted, the expansion would slow. But dark energy adds a repulsive term to the cosmic equation. It doesn't push galaxies the way wind pushes a sail. Rather, it stretches the very space between them. The effect is small on local scales. Galaxies, solar systems, and atoms remain bound. But on vast scales, it dominates. Beyond the pull of clusters, dark energy takes over, driving galaxies away from each other faster and faster. Cosmologists describe the expansion rate with a quantity called the Hubble constant. It measures how quickly the universe grows per unit distance. If two galaxies are 1,000,000 light-years apart, and the Hubble constant is about 70 kilometers per second per megaparsec, they move away from each other at 70 kilometers per second for every megaparsec that separates them. The farther apart they are, the faster they recede. That linear relationship has held since Hubble's discovery, but dark energy changes its slope over time. The expansion is no longer constant, it's accelerating, meaning the slope steepens as the universe grows. The future implications of this are profound. If dark energy remains constant, the expansion will continue indefinitely, and the universe will grow emptier over time. Galaxies not gravitationally bound to ours will drift away beyond visibility. Their light will redshift until it's stretched beyond detection. Over billions of years, the night sky will fade as distant galaxies vanish one by one. Eventually, only our local group, an island of merged galaxies bound by gravity, will remain visible. Everything else will have receded beyond the cosmic horizon. This scenario is sometimes called the Big Freeze. It's not an explosion or collapse, but a slow fading. Stars will burn out, black holes will evaporate, and the universe will cool toward absolute zero. The expansion won't stop. It will simply continue into silence, driven by dark energy's endless push. Time itself will stretch without limit, and space will grow so large that even the faintest radiation will disperse. It's a vision of eternity not filled with fire, but with stillness. There are, however, other possibilities. Dark energy might not be constant. It could change over time, perhaps increasing or decreasing in strength. If it weakens, gravity might eventually slow the expansion again, possibly leading to a collapse. If it strengthens, the acceleration could grow catastrophic, tearing apart galaxies, solar systems, and even atoms in a future event called the Big Rip. In that scenario, the expansion becomes so rapid that it overcomes all forces, ending the universe not with a crunch or a freeze, but with dissolution. Observations so far suggest that dark energy behaves like a cosmological constant, but the margin of uncertainty leaves room for change. The universe could remain calm, or it could end in motion. Even the name dark energy is a kind of placeholder, a way of labelling ignorance. We don't know what it is. It might be the energy of the vacuum predicted by quantum field theory, but calculations from that theory give a value that's enormously larger, by a factor of 10^120, than what we observe. That discrepancy is one of the biggest unsolved problems in physics. The universe's expansion shows that dark energy is real, but our equations fail to explain its magnitude. Some theorists suspect that we're missing a deeper principle, one that connects quantum mechanics and gravity in a way we haven't yet discovered. Until then, dark energy remains an unsolved piece of the cosmic puzzle. Whatever its nature, dark energy changes how we understand the universe's structure. It means that the cosmos is not static or cyclical, but dynamic, with an open future. The expansion doesn't simply carry galaxies apart, it defines what can exist and what can't. As regions drift beyond each other's horizons, they become causally disconnected. Communication, gravity, and light can no longer cross the expanding void. The universe fractures into isolated domains, each one its own self-contained spacetime. It's a quiet fragmentation, invisible but inevitable. That fragmentation has already begun. The galaxies we observe at great distances are receding faster than light, carried by the expansion of space itself. Their light still reaches us now, but the photons they emit today will never arrive. The observable universe is shrinking in content even as it grows in size. Over cosmic timescales, our accessible cosmos becomes a smaller and smaller fraction of the total, confined to a finite region around us, while the rest expands beyond reach. It's hard to appreciate the scale of this process, because it happens so slowly relative to human experience. On Earth, centuries pass and the sky looks unchanged. Even on galactic timescales, the differences are subtle, but given enough time, the effect compounds. 1 trillion years from now, distant galaxies will have vanished from view, their light redshifted into oblivion. The cosmic microwave background too will fade, its temperature dropping below any detectable threshold. The universe will appear dark and empty, though it will still be expanding faster than ever. This might sound like an ending, but in another sense it's just a continuation. Expansion doesn't destroy space, it creates more of it. The universe doesn't run down, it grows thinner. Dark energy's push isn't violent. It's steady, relentless, and indifferent. It's the quiet force that defines the shape of cosmic time. In every moment, more space comes into being, carrying galaxies apart, carrying light into longer wavelengths, carrying the horizon farther away. It's the background motion of existence itself. There's a symmetry between this expansion and the inflation that occurred at the beginning. Inflation drove space apart in a burst that smoothed and flattened everything. Dark energy now drives space apart again, slowly and eternally. In both cases, the mechanism is built into the fabric of reality. The universe begins and ends with expansion, two phases separated by eons but connected by the same underlying principle. That space is dynamic, not static, and that its energy determines its destiny. This understanding changes what we mean when we talk about the universe. It's no longer a single, fixed entity with a beginning, middle, and end. It's a process, an unfolding. It expands not into something, but into itself, generating more space as time passes. The galaxies recede not because they are moving through the void, but because the void itself is stretching. Dark energy doesn't push in the way a force pushes. It expands the definition of distance itself. When you look up at the night sky, every point of light you see is part of this expansion. The space between you and the stars is growing, imperceptibly but continuously. The light that reaches you from distant galaxies carries with it the record of that stretching, encoded in its redshift. Every photon, every wave of radiation is a record of expansion's history. Dark energy's influence is written in the fading of the light, in the increasing distance between galaxies, in the silent growth of the cosmos. The strange part is that this process never stops. As far as we can tell, dark energy doesn't decay or dissipate. It doesn't run out or weaken over time. It's a property of space itself, and as long as there's space, there will be dark energy. that means expansion will continue forever, faster and faster, without boundary. Space will grow emptier but larger, colder but wider. The galaxies will vanish from sight, but the process that carried them away will go on. And yet, within that endless expansion, there's another side to the story. Even as the universe accelerates outward, time continues everywhere, and matter follows its own path within that growing emptiness. The galaxies that vanish beyond the horizon don't stop existing. They go on, evolving in their own regions of space-time, beyond communication, but not beyond reality. The universe's story doesn't end. It simply becomes a collection of parallel, isolated stories, each unfolding beyond the reach of the others. Somewhere, in the unobservable vastness, there are regions where the light of our own galaxy will never arrive. To those distant places, the Milky Way will vanish just as their galaxies vanish to us. The symmetry of this is beautiful in its way. Every observer, everywhere, watches the rest of the universe drift into darkness, never realizing that they too are fading from someone else's view. The expansion is universal, impartial, endless. And beyond that expansion, perhaps even beyond the limits of dark energy's reach, lies something deeper, the question of what it means for the universe to continue forever. If expansion never ends, does time itself have a horizon? Does the universe's story have a final state, or does it dissolve gradually into a silence that never concludes? When we talk about time, we often mean something we can measure, the ticking of a clock, the passing of seasons, the aging of the world around us. But beyond our reach, beyond the faintest light of the farthest galaxies, time goes on without anyone to count it. It flows even where there is no witness, no record, and no memory. The universe does not depend on being seen to continue. Its events unfold regardless of observation, following the same laws everywhere, even in the dark regions where no signal will ever cross again. This idea can be difficult to grasp because human time is bound to experience. Our sense of duration depends on change, on things happening, on noticing the difference between before and after. Cosmic time is not like that. It doesn't wait for attention. It doesn't need consciousness to pass. It moves forward, written into the expansion of the universe itself. As space grows, time grows with it, one dimension stretching alongside the other. Even as galaxies vanish beyond our horizon, their clocks continue to tick. The term cosmic time has a precise meaning in cosmology. It's the time measured by an observer, moving with the expansion of the universe, not rushing through it, but drifting naturally along as space stretches. For us, that's the time that began with the Big Bang, and has flowed ever since, the same cosmic clock that governs everything. It's universal, in the sense that every observer who moves with the cosmic flow experiences the same sequence of events. From the first light to the present, from now to whatever comes next, cosmic time keeps its rhythm everywhere. But in the far future, the flow of that time will continue in silence. Long after the stars fade, after the galaxies grow dim and drift beyond one another's sight, the universe will still exist, but its changes will be slow and faint. The story of creation will have played out, and what remains will be a universe of motion without memory. At that stage, time will still move forward, but the events that mark it will become rare. Entropy, the gradual dispersal of energy, will dominate. Each moment will resemble the next, not because time has stopped, but because there is so little left for time to change. To understand this, it helps to think of time as the measure of difference. Where there is energy, interaction and motion, time is easy to feel. Stars burn, planets orbit, atoms vibrate. Each of these processes marks time in its own way, but as the universe expands and cools, those processes fade. The stars will eventually exhaust their fuel, one by one. White dwarfs will dim, neutron stars will cool, black holes will evaporate through the slow emission of radiation. The The cosmos will lose its bright markers of change. What remains will still experience time, but it will be the time of slow decay, of diffusion and distance, not of creation and light. The disappearance of light does not mean the disappearance of time. Even when all visible energy is gone, quantum processes will continue at the smallest scales. Particles will still fluctuate in and out of existence, energy will still pass through fields, and the expansion of space will still stretch whatever remains. But without witnesses, without structures to record or respond, the flow of time becomes abstract. It is no longer the time of observers, but the time of existence itself. The universe will carry on its silent progression, not paused, not ended, but empty of things that notice. From our perspective, this distant future might seem unimaginable, but the physics that predicts it is the same physics we use to describe the world around us now. Entropy, expansion, and decay are not theoretical. They are the natural consequences of the same laws that govern stars and atoms. The future of the universe is written in the direction those laws always point, toward balance, equilibrium, and the dispersal of energy. Even as space expands faster and faster, that direction does not change. Everything moves toward uniformity. The heat of stars and the cold of voids blend slowly into one even temperature, until no process can extract energy from the difference. Time without witness doesn't mean a lifeless universe. It means a universe beyond observation. Galaxies beyond our horizon will continue to form stars for billions of years, long after their light stops reaching us. In those remote regions, life might arise, flourish, and end, all without ever knowing of us, just as we will never know of them. Their histories will unfold within their own horizons, sealed by expansion, disconnected from ours. For them, time will feel as alive and vivid as it does for us now, full of change and meaning. Only from a broader view, the view of the whole universe, does time seem to continue without notice. Every region carries on within its own limits, while the whole drifts toward stillness. In this way, the universe becomes a collection of separate timelines, each one visible only within its own domain. The galaxies that remain bound together will share a common future, their stars orbiting one another for trillions of years. Eventually, their combined gravity will pull them into a single massive structure. Inside that island of stars, time will continue to be marked by internal events, collisions, novas, black hole mergers, even as the external universe fades. For those who might exist then, the outside world will already have disappeared. Their observable universe will have shrunk to the boundaries of their own galaxy cluster. Their skies devoid of other galaxies, their history cut off from everything else. This isolation is not unique to us. Every observer in every galaxy will face the same fate. Each will see their sky empty, their cosmos shrink, their horizon close in. Yet in every case, time will go on. The universe doesn't end when observation ends. It simply becomes invisible from one place to another. Every region continues its story, though no region can know the others. The expansion of space divides the cosmos not into fragments of matter, but into fragments of history, each one sealed by the speed of light. The notion of time continuing without witness touches on something fundamental about reality. It implies that existence does not depend on perception. The universe would go on whether or not anyone was there to observe it. The light would still travel, even if no one saw it. The stars would still burn, even if no one named them. The equations that describe the cosmos are indifferent to consciousness. They unfold naturally, automatically, with no need for recognition. This doesn't diminish the role of observers, it clarifies it. Observation is local, reality is global. The universe isn't aware of itself, it simply is. That realization brings a kind of calm. It means that even as everything we know changes, the process itself continues. The laws of physics don't end with humanity, or with stars, or with galaxies. They persist beyond the limits of life, beyond the reach of light. Even when the cosmos grows dark, the underlying structure remains. Quantum fields still hum with energy, spacetime still stretches, time still flows. The universe doesn't need activity to endure, it needs only existence. It's interesting to think about how different regions of space experience time differently as expansion accelerates. In relativity, time is not absolute. It depends on the observer's motion and position in the gravitational field. In the early universe, when matter was dense and gravity strong, time ran slightly differently in different places. As the universe thins and expansion dominates, those differences fade. Cosmic time becomes nearly uniform, but in the far future, near massive black holes or other dense remnants, time will slow again relative to the expanding void. Inside those regions, billions of years might pass elsewhere while only seconds tick near the horizon. Even in the final quiet, relativity continues to shape the rhythm of existence. Eventually, if the expansion continues indefinitely, most of what we consider events will cease. No new stars will form, no galaxies will merge. The remaining black holes will slowly evaporate, releasing their energy as faint radiation over incomprehensible spans of time. Each black hole's life will outlast all the stars, but not eternity. When they finally disappear, the universe will consist of thin gas, low-energy particles, and long-wavelength radiation spread over an immense volume. The rate of change will be so slow that for all practical purposes it will seem frozen. Yet even then, time will still move forward. The expansion will continue. The geometry of space will keep evolving, even if the difference from one moment to the next becomes imperceptible. If dark energy remains constant, this process will never end. The horizon will shrink in relative terms until every region of the universe is causally isolated. Each patch will expand into its own eternity, unaware of the others. Within each, time will continue without limit, but the events that mark it will vanish. It's a strange sort of immortality, not the persistence of things, but the persistence of process. The universe doesn't die, it fades into a state of almost perfect equilibrium where everything that can happen has already happened, and what remains is the continuation of expansion itself. When we think of time without witness, we tend to imagine emptiness, but there is still structure in that future. The quantum fields that fill space never become truly still. They fluctuate randomly and continuously. Even in a universe approaching heat death, those fluctuations will persist. Over unimaginably long spans, they might even produce rare pockets of structure again. Tiny bursts of energy, new beginnings that form spontaneously. Some physicists speculate that such fluctuations could give rise to new universes, small bubbles that start inflating just as ours once did. If so, the process of creation never stops. The universe may continue to generate new regions of space-time forever, each with its own arrow of time. In that sense, time without witness could also mean time reborn elsewhere. The picture that emerges is not one of an ending, but of transformation. Time doesn't vanish, it stretches and thins, like light redshifting toward infinity. The witnesses come and go, but the flow remains. Even when everything quiets, the framework endures. Space-time, energy, and the laws that bind them continue, unobserved but active. The universe carries on without an audience, writing its history into a book that no one will ever read, but that still exists in full. If the universe continues beyond our perception, does that mean our understanding is incomplete, or simply local? Is the edge of our knowledge the edge of reality, or just the edge of our horizon? Every discovery the universe has allowed us to make has been shaped by one unspoken truth. We can only know what we can see, and what we can see is always less than what there is. The limits of knowing aren't just a matter of technology or imagination. They're built into the structure of the universe itself. Light takes time to travel, space stretches faster than signals can cross, and the laws of physics forbid certain information from ever reaching us. What we call the universe is really a fragment of something larger, a visible island in a sea of unobservable reality. The edge of the observable universe is about 46 billion light-years away in every direction. That number alone is misleading, because it's not a measure of age but of distance as stretched by expansion. The light we see from those farthest galaxies began its journey over 13 billion years ago, when the universe was young. In that time, space has expanded, carrying those galaxies far beyond the reach their light once bridged. The image we receive of them is a message from the past, not a current snapshot. In fact, most of what we see in the cosmos doesn't exist anymore in the form we see it. The light that reaches us now left its source long ago, and in the time since, entire galaxies have changed, stars have burned out and clusters have shifted. What we study is not the present universe, but its long exposure photograph. This limitation is not an obstacle in the usual sense. It's a fundamental feature of reality. The finite speed of light means that we can never observe the universe as it is, only as it was. Every telescope, no matter how powerful, is also a time machine. The deeper we look into space, the further back we see in time. There's no way around it. Even the nearest star, Proxima Centauri, is more than 4 years away in light travel time. The sunlight you see now left the sun 8 minutes ago. The image of the Andromeda galaxy shows how it looked 2.5 million years in the past. There's no possible observation of now on a cosmic scale. Now is local, confined to wherever you are. In this sense, knowledge of the universe is always historical. Every piece of data we collect is a record from a different era, and we piece those records together to reconstruct a coherent picture. We have no direct access to the present state of distant galaxies, and certainly not to the future. Yet the structure that emerges from those pieces is remarkably consistent. The universe behaves according to patterns we can describe, and those patterns hold across scales and epochs. That consistency is what makes science possible. The fact that the laws governing a hydrogen atom here and now are the same laws that governed hydrogen at the dawn of time. Still, even that faith in consistency has its limits. We infer the uniformity of physical laws beyond observation, because it makes sense of the data we can see, but we can't prove that it holds everywhere. There could be regions beyond our horizon where conditions differ, where the constants of nature take on slightly different values, where the forces that shape matter behave in unfamiliar ways. Inflation theory, which explains the smoothness of our universe, also predicts that the broader cosmos could contain vast differences between regions. Each one could have its own version of physics, born from quantum fluctuations during inflation. If so, then our understanding of universal laws is actually a local truth, not an absolute one. Even within our observable region, there are barriers to complete knowledge. We can't see through dust clouds in our own galaxy without infrared instruments. We can't directly observe the interiors of stars or the hearts of black holes. We can't measure dark matter except through its gravitational effects, and we can't detect dark energy except by observing how the universe expands. Much of what we know is indirect, inferred from its influence on what we can measure. Science, in that sense, is a constant negotiation with limits. It's the art of learning from what we can't see by studying how it shapes what we can. Those limits aren't just physical, they're mathematical. Even our best theories are approximations of reality. General relativity describes gravity on cosmic scales, and quantum mechanics describes the behavior of particles on the smallest scales. Both have been tested with extraordinary precision, yet they are incompatible in their current forms. Somewhere between the very large and the very small, our models stop agreeing. The unification of these theories, a complete description of nature, remains out of reach. The boundary between them is another kind of horizon, not in space but in understanding. At the core of this gap lies an even deeper question: whether the universe can ever be fully knowable at all. The idea of a complete theory of everything, a single equation that describes all phenomena, has driven physics for decades. But the more we learn, the more it seems that each answer opens new layers of mystery. Quantum mechanics itself tells us that uncertainty is not just a limitation of measurement, but a property of nature. The Heisenberg uncertainty principle states that certain pairs of properties, like position and momentum, can't be precisely known at the same time. The act of measurement defines what can be known and excludes what can't. Knowledge and ignorance are two sides of the same process. On the largest scales, a similar uncertainty appears. The accelerating expansion of the universe creates a cosmic event horizon, beyond which information can never reach us. It's not a temporary barrier, it's permanent. No future observation, no matter how advanced, will ever reveal what lies beyond. The cosmos hides most of itself behind a curtain woven from its own geometry. The more it expands, the less we can see. Every second, light from more distant regions falls out of reach, swallowed by expansion faster than it can travel. The universe is actively increasing its own unknowable volume. This means that the boundary of knowledge isn't just fixed, it's moving. Our observable universe changes over time. The galaxies we can study today will one day be gone, their light stretched beyond detection. The cosmic microwave background, the oldest light we can see, will eventually fade as well. The further into the future we go, the smaller the universe will appear to any observers who remain. They'll live in a cosmos of isolation, unaware that it was ever larger. Their knowledge will be bounded not by their tools but by physics itself. Even within our current horizon, the picture is incomplete. The visible matter in the universe accounts for only a small fraction of its total mass and energy. The rest is dark. We can map where dark matter must be, because we can see how its gravity bends light and affects the motion of galaxies. But we don't know what it is. The particles that make up dark matter have never been directly detected. The same is true for dark energy. We know it accelerates the expansion of space, but we don't know its cause or composition. Our most successful cosmological model, the lambda CDM model, rests on components that are largely invisible and unexplained. We can describe their effects precisely, but their nature remains beyond our grasp. These limits are not failures of science, they are its frontier. Every unanswered question defines the edge of knowledge, the boundary between what we understand and what we still seek. That boundary is not fixed either. It moves as we learn. A few centuries ago, the size of the Milky Way was thought to be the size of the universe. A century ago, the expansion of the cosmos was unknown. Each discovery pushes the horizon outward, but the horizon itself never disappears. The universe always has more to show, or rather, more that it hides. It's easy to imagine that someday, with enough technology, we'll know everything there is to know. But that hope assumes the universe is finite, and that knowledge has an endpoint. The evidence suggests otherwise. Even if we mapped every galaxy in the observable cosmos, we'd still know almost nothing about what lies beyond it. Even if we unified gravity and quantum mechanics, there would remain questions about why the universe exists at all, why its laws take the form they do, why there is something rather than nothing. Those questions may not have answers that fit within science, or perhaps they do but remain forever outside our reach. There's also the question of whether the act of knowing itself changes what can be known. In quantum physics, observation affects outcomes. In cosmology, observation defines perspective. Our instruments extend our senses, but they also anchor us in our own region of space-time. We can never see the universe from the outside. We can only see it from within, bound by its geometry and history. Every measurement we make is shaped by where and when we exist. The data we collect is local, no matter how vast our telescopes. These constraints might sound limiting, but they are also what make knowledge meaningful. To know something at all, there must be something unknown beside it. The limits define the act of discovery. Without mystery, curiosity wouldn't exist, and without curiosity, knowledge would have no direction. The cosmos offers endless opportunities to learn, precisely because it withholds as much as it reveals. Every observation is both an answer and an invitation. Perhaps that's the most important lesson in the limits of knowing, that understanding the universe is not about reaching a final truth, but about exploring an infinite one. The purpose of inquiry is not to finish the map, but to keep extending it, even knowing it will never be complete. Each new discovery changes the edge of the known, and that edge keeps moving forward into the dark. The boundaries of knowledge, like the boundaries of the observable universe, are not barriers in the traditional sense. They are horizons, dynamic, relative, and constantly shifting. They move as we move, defined by light, time, and the speed of thought. To approach them is to accept that there will always be more beyond, more to wonder about, more to seek. The limits are not a failure of human understanding. They are a feature of reality itself. They ensure that the story continues. When we look out into space, we are not seeing distance so much as duration. Every point of light in the sky carries with it a measure of time, a story told in photons that have travelled across billions of years to reach us. The further we look, the further back we see. The night sky is not a map of where things are, but of where they were. In that sense, the universe we observe is not the universe as it exists now, but a layered record of its own past. A kind of cosmic memory written in light. This is one of the most fundamental truths in cosmology, and also one of the hardest to truly feel. When we look at the sun, we're seeing it as it was 8 minutes ago. When we look at the nearest star, we see it as it was 4 years ago. When we observe galaxies through a telescope, we are looking millions or billions of years into their past. The further the object, the older the light. Some of the galaxies whose light reaches us tonight no longer exist as we see them. They may have merged, transformed, or faded entirely. Their light continues to travel through space, unchanged, a signal from a version of the universe that has long since moved on. The entire observable universe is a time capsule. The light from distant galaxies was emitted when the universe was young, when stars were forming at a furious rate and matter was more densely packed. The cosmic microwave background, the faint radiation that fills the universe in every direction, is a remnant from the time when the cosmos was only about 380,000 years old. To detect it is to see the afterglow of a moment when atoms first formed and light was able to travel freely through space. Every observation, from nearby stars to ancient radiation, is a glimpse into the universe's history. This layering of time means that space is not a single, simultaneous reality. It is a mosaic of different eras, all visible at once from our vantage point. The light from a galaxy 10 billion light-years away left when the universe was young, while the light from a nearby star left just moments ago. Both arrive at the same instant, overlapping in our view. The sky is therefore a mixture of past events, each photon a messenger from a different moment. To look outward is to look backward through the universe's timeline, one layer at a time. In that sense, the universe is always looking back at itself. Every photon of light emitted by a star, reflected by a planet, or scattered by a cloud of gas is a piece of information about its origin. Those photons travel outward forever, carrying the memory of what was. Some of them are absorbed or deflected, but many continue, moving through expanding space until they are so stretched by redshift that their energy fades into the background. Even then they still exist, preserving the imprint of their source in the endless flow of radiation. The universe is full of these imprints, crossing paths, merging and fading, forming a kind of archive that no observer could ever fully read, but that still exists everywhere. This idea becomes clearer when you consider how we detect distant light. A telescope doesn't capture the present, it collects the past. The light that enters the instrument has travelled across time and space, carrying with it the conditions of its origin. By studying its spectrum, how its wavelengths are stretched or compressed, astronomers can tell how fast the source is moving, how far away it is, what elements it contains, and how old the light is. Every image is an act of translation, converting ancient photons into present understanding. It's a quiet paradox. The farther we look into space, the younger the universe becomes in our view. We see galaxies as they were billions of years ago, clusters forming from primordial gas, the first stars igniting. The most distant galaxies detected by telescopes like the James Webb are seen as they existed less than 500 million years after the Big Bang. Beyond them lies the faint glow of the cosmic microwave background, which marks the limit of what light can show us. There is no earlier light to detect, because before that time the universe was opaque, a dense plasma where photons scattered endlessly and could not travel freely. To see beyond that would require a different kind of observation, one that senses not light but the imprint of gravitational waves from the earliest moments of expansion. In this way, the universe reveals itself gradually, one epoch at a time. We reconstruct its history by reading the light that has reached us, like decoding messages from the past. The galaxies we see at various distances show how structure evolved, how matter clumped under gravity, how gas condensed into stars, how heavy elements formed and spread. Each observation fills in another piece of the timeline, another step in the universe's long unfolding. But even this process has limits. The further back we look, the harder it becomes to distinguish details. Light is faint, red-shifted and distorted by intervening matter. Eventually the signals blend into noise and the picture dissolves. Beyond that, there is only inference, equations and models that describe what must have happened before the first light could shine. The fact that we can see so much of the universe's past is itself remarkable. Photons have been travelling since the first atoms formed, and space has been stretching around them all the while. As the universe expands, those photons are stretched too, their wavelengths lengthened, their energy lowered. The light that began as visible radiation from early stars is now infrared. The light that began as high-energy radiation from the early plasma is now microwave. Expansion turns brightness into faintness, colour into coldness and heat into silence. Yet the information remains, it just changes form. If you think about it, the light reaching Earth from the cosmos is an unbroken link between us and the universe's entire history. Every photon that touches your eye or a telescope mirror has travelled across ages, through the growth of galaxies, through clouds of interstellar gas, through the quiet emptiness of expanding space. Some of those photons were emitted before the Sun existed, before the Milky Way had its current shape, before any life on Earth began. To observe them is to receive the universe's oldest stories. They are not metaphors. They are real fragments of time that have crossed billions of years to arrive here. And because the universe has no centre, this act of looking backward is symmetrical. From any galaxy, anywhere, an observer would see the same thing. A universe filled with ancient light, receding galaxies, and a cosmic background that marks the beginning of visibility. Every point in space is the centre of its own observable universe, surrounded by a sphere of time. When we gaze outward, the universe gazes back from every other point, each one with its own horizon, its own record of light. The entire cosmos is full of these mutual views, none privileged, all equally valid. The universe, in this sense, is looking back at itself from every direction. Through every observer that ever was or will be, there is something quietly reassuring about this symmetry. It means that our perspective, while unique to us, is not special in its structure. The same physical laws, the same relationship between distance and time, the same horizon of light apply everywhere. Every observer, wherever they may be, sees a universe expanding away from them, filled with the glow of its own past. The cosmos doesn't play favourites. It presents itself equally to all who can look. The light we see from the past also tells us about the future. The expansion of space stretches not only distance but destiny. When we measure the redshift of distant galaxies, we are measuring how fast they are receding. The faster the redshift, the farther they are, and the faster they are being carried away. By tracing this relationship, astronomers can calculate how expansion has changed over time and how it will continue. The universe's acceleration, driven by dark energy, means that the light we see now from many galaxies will be the last light we ever receive from them. As expansion continues, those galaxies will drift beyond our horizon, their light stretched into wavelengths too long to detect. They will disappear, not by dimming, but by distance. This makes every photon that reaches us now even more significant. It's not just light from the past, it's a finite connection to regions of the universe we will soon never see again. Each observation we make adds to a record that future observers won't be able to replicate. The universe is not static, it's in the process of erasing its own visibility. What we see today is a temporary window in cosmic time, a moment when light still bridges the gaps between galaxies. In the future, those bridges will break. The light that connects us to the wider cosmos will fade, and only local structures will remain. Even so, the universe's ability to look back at itself doesn't disappear. It simply becomes local. The galaxies that remain bound together, the ones that share gravity's hold, will continue to exchange light for trillions of years. Within those regions, time will still be visible. Stars will rise and fall, planets will orbit, radiation will travel. The flow of information will persist within each gravitational island, even as the larger connections vanish. Each island will become a small universe unto itself, a place where the past can still be seen, even as the rest of the cosmos fades from view. There is a quiet continuity in that process. The universe never stops looking back at itself. It just changes the scale on which it does so. In the early universe, light connected everything. Every region could see every other region. As expansion progressed, that visibility narrowed, confining observation to smaller and smaller domains. The pattern continues, but the principle remains the same. Wherever there is light and an observer to receive it, the universe continues its reflection. And even in the final quiet, when no observers remain, light will still travel. It will still carry the memory of its source across the growing emptiness. It will still redshift, fade, and stretch, preserving in its structure the story of where it began. The universe's act of looking back doesn't depend on anyone watching. It's built into the physics of radiation, the constant exchange of energy across space. The cosmos is a self-illuminating record, written not for anyone, but by the act of existence itself. It's strange to realize that the more we look outward, the more we also look inward. Every observation tells us not only about distant galaxies, but about our place in time, our role as one more point of reflection within an ongoing process. We are part of the universe's ability to look back at itself. Every instrument we build, every photon we catch, adds to that reflection. The act of observation is an extension of the universe's memory, an echo of its earliest light interpreted by minds that arose from the very matter that light once illuminated. And yet, even as we see the universe's past in its glow, there is always something beyond the reach of light, something that remains unseen, unobservable, and perhaps unknowable. Beyond every horizon lies more universe. Beyond every faint photon lies another region that light will never cross. The question that follows is simple and inevitable. If there is so much beyond our view, if the visible universe is only a fragment of an unending whole, what does that say about our understanding of infinity itself? The idea of infinity is not something the mind can comfortably hold. It stretches thought past the point of structure, beyond the boundaries of comparison or measurement. Yet when we talk about the universe, its scale, its age, its continuation beyond what can be observed, infinity appears again and again, quietly built into the equations that describe reality. The universe might be finite in what we can see, but the mathematics of cosmology leaves open the possibility that it has no edge, no boundary, and no end. What began as a single expansion could be a process without conclusion, continuing forever in space and time. When scientists describe infinity in cosmology, they don't mean something mystical, they mean something precise, a universe that has no limits in extent, no outer surface, no final point. Space could curve back on itself like the surface of a sphere, or it could extend endlessly in all directions. Both options are consistent with the data we have. The cosmic microwave background shows that space is flat to an extraordinary degree, not perfectly, but so close that if it is curved, the radius of that curvature is larger than the observable universe. That means the universe could be effectively infinite. We might live in a small part of an unbounded whole, a region where every direction extends forever. To think about infinity in this way is to accept that there may be no totality to the universe, no final all that can be measured. Whatever we can see is only a part, and there may always be more beyond. The observable universe, immense as it is, might be an infinitesimal patch on an infinite surface. And that surface could contain endless variations, endless galaxies, endless stars, each existing in its own position and time. In such a universe there would be no edge to reach, only more of the same repeating in every direction. If the universe is infinite, then the implications are difficult to fully absorb. For one, it would mean that matter, though finite in any local region, could repeat in pattern across the infinite. Given enough space, even the rarest arrangements would occur somewhere. Every possible configuration of matter would exist, not once, but infinitely many times. Somewhere, unimaginably distant, there could be another region of space identical to ours, with another Earth, another solar system, another set of people having this same thought. It's not fantasy, it's a statistical consequence of infinity. If the laws of physics are uniform everywhere, and the combinations of particles are finite, then infinite space guarantees repetition. Of course, none of this can be proven. It's beyond observation by definition, but the mathematics makes it plausible, and the universe's flatness supports it. Even if the universe is not infinite in space, it could be infinite in time. The expansion driven by dark energy ensures that space will continue to grow indefinitely. Even as matter thins and galaxies vanish beyond each other's reach, the expansion itself never stops. Time stretches endlessly forward, carrying space with it. The universe does not loop back or reset, it continues. The infinity of duration replaces the infinity of distance. It's tempting to imagine that infinity must be a kind of perfection, that it completes something finite by extending it without limit. But infinity is not completion, it's continuation. It's the refusal of any process to reach an end. In the universe, this continuation takes many forms. The expansion of space is infinite in potential. The division of time is infinite in precision. The number of possible positions or energy states for particles is infinite in concept. Every equation describing the cosmos reaches toward infinity at its boundaries. The universe is not infinite in every measurable sense, but it contains infinity as a structural possibility, an idea that recurs wherever we try to define its limits. Infinity also appears in the smallest scales. The quantum world is not smooth but probabilistic. Space and time might be quantized, made up of discrete units smaller than we can ever detect. Yet the number of ways those units can combine, the number of possible interactions and outcomes, is infinite. In that sense, infinity is not about size but about possibility. The universe, whether finite or infinite in extent, contains endless combinations within itself. Every atom, every fluctuation, every quantum field can vary in countless ways. The total number of potential states exceeds comprehension. The human mind wasn't built to process infinity directly. Our sense of scale is anchored to what we can touch, measure, and compare. When numbers grow too large, they lose meaning. We can say a trillion, or a quadrillion, or a Google, but beyond a point those words become placeholders for more than we can imagine. Infinity is the ultimate placeholder. the point at which quantity stops being a number and becomes a condition. In mathematics, infinity is not a value, but a direction. In physics, it's the limit that describes where equations stop working. The concept tells us that the universe is not contained within the boundaries of simple numbers. Still, infinity has consequences for how we think about existence. If the universe has no limits, then there is no privileged position within it. Every region of space is equally valid, equally central. The cosmos looks the same from every vantage point on large scales, not because we are at the centre, but because there is no centre. This symmetry is one of the cornerstones of cosmology. It's called the cosmological principle, and it reflects the idea that the universe is homogeneous and isotropic when viewed over large distances. Infinity supports that symmetry. Without edges or boundaries, space is self-consistent everywhere. For most of human history, the idea of infinity was philosophical, not physical. It belonged to mathematics, not to the sky. The visible universe seemed finite. The stars occupied a dome, the earth had a horizon, the heavens appeared contained. Only in the modern age, with telescopes and theory, did infinity become part of science. When Hubble discovered that the universe was expanding, the idea of a beginning replaced the idea of an eternal static cosmos. Yet even with a beginning, the universe could still be infinite. Expansion doesn't require an edge, it requires motion. The universe can grow forever and still have no boundary. This infinite continuation has a quiet consequence for meaning. If there are infinite regions of space and time, then everything that can happen might happen somewhere. The uniqueness of events becomes local, not absolute. Our existence, our planet, our history, could be one of countless versions. Infinity erases the notion of rarity. It replaces once with always. But it also removes the notion of completion. There is no total universe to count, no final state to reach, no ultimate answer to find. Every observation, every law, every structure is one expression within an unending whole. For scientists, infinity is both a tool and a warning. It allows equations to describe continuous phenomenon, but it also signals where theories break down. When a calculation produces infinity, infinite density, infinite curvature, infinite energy, it usually means we've reached the limits of our model. The centre of a black hole, where general relativity predicts infinite density, is a sign not of reality's infinity, but of the theory's incompleteness. The Big Bang, when traced backward to a singularity, raises the same issue. Infinity in practice often marks the edge of understanding. It's the point where our language stops. In that sense, infinity is as much a symbol of ignorance as of vastness. It represents the horizon of comprehension, the place where we can go no further with the tools we have. Yet that horizon keeps moving. Every time we learn something new, what lies beyond becomes a little clearer, and the boundary of infinity shifts outward. It's not that infinity retreats, it's that our understanding grows within it. The more we know, the more we realize how much remains unknown. Infinity expands not in defiance of knowledge but in step with it. Still, there is a quiet comfort in the idea that the universe might have no end. It means that discovery never stops. It means that even as light fades and galaxies drift apart, there will always be more beyond what can be reached. The cosmos doesn't run out of itself. It continues into regions beyond perception. The horizon of the observable universe is not the horizon of existence. Infinity ensures that there is always more to imagine, more to infer, more to wonder about. If infinity applies not only to space but to time, then the universe's story also has no final page. Even if stars burn out and matter decays, time itself may continue. The expansion may go on forever, carrying space into ever greater stillness. New fluctuations could arise, new regions could inflate, new universes could form. In that way, infinity connects the beginning to the continuation, linking the first moment of expansion to the possibility of endless creation. The universe might not just last forever, it might keep generating new versions of itself. To think about this too deeply can make the mind falter. There's no frame of reference for infinity, no point of completion from which to describe it. But the purpose of science has never been to comprehend everything at once. It has been to understand enough to keep asking questions. Infinity ensures that there will always be questions left to ask. It preserves curiosity by guaranteeing that the unknown will never end. Even if the universe is finite, the infinite appears within it, in the divisions of time, in the precision of numbers, in the recursion of structures. The infinite is embedded in the finite, just as the horizon is embedded in the visible sky. You can't reach it, but it defines what you can see. Infinity doesn't mean endlessness in every direction. It means that there is no limit to what can be understood next. And so, as the universe expands and light fades, the dream of the infinite remains. It's not an idea of boundlessness in space alone, but of continuity and understanding. Each generation of observers sees a little farther, learns a little more, pushes the horizons slightly outward. Infinity is not a goal to reach, but a condition to exist within. The cosmos doesn't end, it deepens. There is a place in thought where words begin to lose their edge, where description thins like starlight crossing distance. The universe reaches that point too. The farther we follow its expansion, the quieter it becomes, not because it ends, but because it stretches beyond the scale where events have a rhythm. The quiet beyond is not a realm separate from the universe. It is the universe continued, carried so far into stillness that its motion becomes imperceptible. It is not absence, and it is not peace in the human sense. It's simply what happens when time outpaces change. Imagine a night sky in a distant future, so far ahead that the galaxies we now see have long since drifted beyond reach. The Milky Way and its neighbours have merged into one vast, slow-moving structure, a single island of stars adrift in dark energy's endless expansion. Beyond that island, there is nothing visible. The light from other galaxies has redshifted into wavelengths too long for any detector to perceive. The cosmic microwave background, once the faint glow of creation, has stretched into radio waves of unimaginable length, so faint that they blend with the whisper of the vacuum. For any observer alive in that distant time, the sky would be almost blank. The universe would seem small, quiet, and alone. But it wouldn't be empty. The space beyond that blankness would still exist, still expanding, still filled with energy too thin to notice. Particles would still move, though so far apart that their interactions would be rare. The fabric of spacetime would continue to stretch, carrying everything farther apart. The laws of physics would still operate, silent and precise, keeping their balance even in the absence of witnesses. The quiet beyond is not death, it's continuation without disturbance. On the scale of galaxies, this process takes unimaginable spans of time. Stars that still shine today will exhaust their fuel, leaving behind white dwarfs and neutron stars. Over trillions of years, even those remnants will cool, fading into darkness. What remains will be black holes, slowly evaporating through the faint release of radiation predicted by quantum mechanics. One by one, they too will vanish, returning their mass to the emptiness as energy spreads so thin it can never gather again. The universe will lose its bright points of reference, but it will not stop. The expansion will continue forever, a process without an audience. This future is not something to mourn. It's simply the natural consequence of the same laws that gave rise to everything we see now. The energy that drives stars to shine also ensures they will one day fade. The expansion that allowed galaxies to form also guarantees they will drift apart. The same order that makes the universe coherent also limits what can last. Entropy, the tendency toward equilibrium, is not a flaw. It's the process by which energy spreads, by which balance is restored. The quiet beyond is the universe's long return to uniformity. It's difficult to imagine such stillness, because our sense of existence depends on motion, on contrast, on the presence of change. But from a cosmic perspective, stillness is not static. It's filled with activity too slow to see. Space itself will continue to stretch, and quantum fields will continue to fluctuate. Even in the coldest vacuum, particles will appear and vanish, borrowing energy from nothing and returning it again. The universe never stops moving at its foundations. The quiet beyond is not the end of activity, but the disappearance of structure. The orchestra continues, but all the instruments are playing below the threshold of hearing. If you could travel far enough into that future, you would find that time still exists, but it has lost its familiar markers. Without cycles of stars or orbits of planets, time becomes purely geometric, the unfolding of space itself. Distances grow, but there is nothing left to measure them by. The universe becomes a landscape without landmarks, a continuity of expansion with no event to punctuate it. In that sense, time and silence merge. They are both extensions of process, not things that happen, but conditions that remain. For any being that might exist then, thought itself would require adaptation. The universe would offer no external cues, no sunrise or sunset, no nearby galaxies to study. Knowledge would be limited to what was already known, memory preserved only in archives that might outlast the stars. The act of looking outward would yield nothing new, because there would be nothing left to see. Even so, the fundamental constants, light's speed, gravity's pull, the structure of space, would persist. The cosmos would still hold meaning in its laws, even if those laws no longer produced visible forms. From our current point in time, the quiet beyond sounds like an ending because we measure stories by beginnings and conclusions. But the universe does not tell its story that way. It doesn't close its chapters, it continues them until they fade into one another. The Big Bang wasn't a single event, but a condition that still echoes in expansion. Likewise, the final stillness is not a conclusion, but the next phase of the same process. If the universe has no boundaries in space, it may have none in time either. The quiet beyond could last forever, not as stasis, but as unending unfolding at infinite slowness. There are still other possibilities hidden in the physics. Some theories suggest that the quantum fields underlying the universe might not stay quiet forever. Over unimaginable timescales, random fluctuations could create new regions of high energy, tiny points that begin to inflate just as our universe once did. If that happens, new universes could be born within the old, each with its own space, its own time, its own story. The quiet beyond might not be the final state, but the womb of new beginnings. The cycle could continue endlessly, one universe giving rise to another. In that picture, the quiet beyond is not stillness but transition. It's the interval between chapters in a book with no final page. Each universe expands, cools and quiets, only for another to begin elsewhere in the vastness of possibility. The overall process never ends, it only shifts form. Creation and silence become partners in a rhythm that has no starting point and no conclusion. What we call the universe might be just one movement in an infinite symphony of beginnings and dissolutions. And yet, even if such renewal never occurs, even if the quiet beyond lasts forever without change, there is something deeply complete about it. The same physical laws that allow for structure also allow for its fading. The same balance that created galaxies allows their light to redshift into invisibility. Nothing in the universe is wasted. It only transforms. The energy that once formed stars and life and thought remains, dispersed into forms that no longer gather, but still persist. The universe does not lose itself. It just spreads itself thinner, until everything that was distinct becomes part of a single, continuous field. In that final state, the universe becomes perfectly symmetrical. Every direction is the same, every point is equivalent. The differences that once defined matter and energy vanish into uniformity. This uniformity is not emptiness, it's equality. It's the completion of entropy's long project, the state toward which all physical processes tend. In that symmetry, there is no more potential for work, no more imbalance to drive change, but the fabric of existence remains. It's a balance that doesn't end, but simply is. To think about this is to realize that the universe doesn't need witnesses to endure. Observation is a local event confined to the brief intervals when light and consciousness coexist. The quiet beyond is not aware, but it is not nothing. It's the continuation of the same existence that has always been, just in a state where awareness is no longer possible. The cosmos doesn't cease when perception fades. It continues in accordance with its laws. The story of the universe is not the story of its observers. It's the story of the laws that govern everything, whether seen or unseen. In our era, we live in a privileged moment, a time when the universe is still visible, when galaxies still shine, when cosmic history can still be traced through light. It will not always be so. The era of visibility is temporary, a phase between opacity and silence. The early universe was too dense for light to travel. The far future will be too diffuse for light to matter. We exist in the middle, in the brief interval where the universe can see itself. That's what makes our observation special. We are part of the universe's self-awareness, the means by which it looks back before it fades into quiet. But the quiet beyond is not loss, it's balance restored. It's what happens when every force, every interaction, every imbalance runs its course. The universe began in expansion, in a symmetry, in difference. It ends in equilibrium, in the smoothing of those differences, in the long drift toward stillness. It's not destruction, it's fulfillment of the same process that started everything. The cosmos is not undone, it's completed in a way that requires no intention and no purpose. Even so, it's natural to wonder whether there's meaning in that stillness. Meaning, after all, is a human construction, born from awareness and comparison. But if meaning depends on contrast, on difference between what is and what is not, then perhaps the universe's quiet is the one condition beyond meaning. It's not meaningless, it's simply beyond the frame where meaning applies. It's the state where being no longer needs to describe itself. If someone could stand in that distant epoch and think, they would find the same equation still valid, the same constant still in place, the same rules still governing the faint remnants of existence. They would know that everything which ever happened remains encoded in the structure of spacetime, preserved as curvature and energy, never truly lost. In that sense, the quiet beyond is not amnesia, it's memory distributed evenly, written everywhere, but so diluted that no part can read it. The information is still there, but no one remains to interpret it, and perhaps that's fitting. The universe doesn't need an audience to be complete. It doesn't depend on awareness to be whole. The quiet beyond is its natural state, the condition that follows from the same principles that made life possible. It's the long, unbroken continuation of what began in light, carried out to infinite stillness. Every star that ever shone, every planet that ever formed, every being that ever looked up, all returned to that state, their matter and energy diffused into the same field. The universe doesn't end, it becomes everywhere at once. Somewhere in that endless continuation, the expansion still unfolds, slow beyond reckoning, calm beyond sound. Space grows, time stretches, and existence persists without event. It's not the end of the story. It's just the part of the story where motion becomes too slow for chapters. The universe carries on, quiet but never gone, vast but indivisible. The same process that began in fire now extended into stillness. And if there is any peace to be found in knowing that, it might come from this, that nothing is truly lost, that every light ever shone still exists somewhere, stretched thin but unbroken, travelling forever into the quiet beyond.